Ben, bo día, imos dar comenzo a apertura desta conferencia final do Plan Complementario de Comunicaciones Cuánticas en Galicia. Bueno, teño o prazer de, como reitor da Universidade de Vigo, actuar como anfitrión, pero teño que decir que a miña satisfacción é contar aquí na mesa de presentación, en primeiro lugar, coa directora da GAIN, con Carmen Cotelo, que nos está axudando en moitas das iniciativas que se queren levar a cabo a nivel galego, e co representante do Ministerio, Jesús María Salvador Sánchez, que é asesor científico do Ministerio de Ciencia, Innovación e Universidades, e que, por suposto, é impulsor destes planes complementarios que se fan ao limón entre o Goberno de España e o Goberno galego. E a miña esquerda está, como ben coñecedes, Marcos Curty, un científico brillante que ademais está collendo o pulo de facer que isto sexa unha realidade, membro de AtlanTTic, creador e director do propio laboratorio relacionado coas comunicacións cuánticas, e que tamén está axudando moitísimo. En teoría, eu teño que falar ao final, ou seña que case primeiro vou a darlle a palabra a Carmen Cotelo, directora da GAIN. Carmen, cando queiras.
Gracias, reitor. Vamos a coller este, sí. Non sei se me escoita. Encender creo que non encendiu, pero escoitades. Desculpas. Pois moi bons días a todos e a todas, reitor, representante do Ministerio de Ciencia, Innovación e Universidades, coordinador científico deste Plan Complementario de Comunicacións Cuánticas e a todos os asistentes na sala, pois moi bons días a todos, moi benvidos a este evento de presentación final deste plan. Para min é unha alegría poder acompañarvos nesta conferencia final na que se van a presentar esos resultados do Plan Complementario de Comunicacións Cuánticas que se le van desenvolvendo en Galicia estes anos. Un plan que forma parte deses 8 plans complementarios de +D+I que se impulsaron desde o Ministerio de Ciencia, Innovación e Universidades en colaboración coas diferentes comunidades autónomas, co fin de fortalecer áreas estratégicas en investigación e innovación en España. Nós, desde Galicia, participamos en 4 desos plans complementarios. Un deles, o Plan Complementario de Comunicacións Cuánticas que hoxe nos trae aquí, e que son os plans que, como adiantaba o reitor, están cofinanciados entre os fondos de recuperación a través do Ministerio e tamén a cofinanciación da Xunta de Galicia, ese apoio que prestamos con fondos propios. E que, gracias a este esforzo conxunto, durante estes 4 últimos anos en Galicia, douse un paso decisivo no desenvolvemento do que ten que ver coas tecnoloxías cuánticas, neste caso das comunicacións cuánticas, contribuindo a ese reforzo cara a ciberseguridade en xeral en Europa e en concreto en España. As comunicacións cuánticas non vou dicir moito do que son, porque creo que calquera dos que está nesta sala pode dicir moito millor cales son as bases desta prometedora tecnoloxía que ten tanta relevancia no ámbito da ciberseguridade, sobre todo nun momento en que vivimos nunha economía e unha sociedade totalmente digital, co cal a ciberseguridade e a seguridade pasan a ter un papel clave, e entón estas tecnoloxías de comunicacións cuánticas traenos unha nova porta a que explorar, tanto para o seu uso como a oportunidade que temos en Galicia de desenvolver estas tecnoloxías, de ser parte activa. E, é un salto científico-tecnolóxico importante que está a transformar esa forma que temos de entender as comunicacións e a seguridade digital. Gracias a esa colaboración interregional con outras comunidades autónomas, neste caso 5, Madrid, Cataluña, País Vasco, Castela e León e tamén a Comunidade Valenciana, colaboración co CSIC, a participación das 3 universidades públicas galegas e o Centro de Supercomputación de Galicia, neste caso na parte do plan complementario que se desenvolveu aquí en Galicia, España e Galicia está se situando nunha posición de referencia internacional neste ámbito, e veño máis convencida a decir isto do que viña, porque tivemos a oportunidade de ter unha pequena visita agora aos laboratorios do Vigo Quantum Communication Center e a verdad que estou moito máis segura aínda de dicir isto con total propiedade, non? Que non lo contaba un pouco o equipo que nos enseñou os 3 laboratorios e o equipo que estaba participando tamén neste plan complementario, que temos esa posición tremendamente relevante no panorama internacional co traballo que se está facendo aquí, moito en gran parte pois aos instrumentos e ao que aportou o plan complementario permitindo pois montar esos laboratorios, atraer persoal, empezar a traballar colaborativamente en distintos aspectos clave que teñen que ver todos coa ciberseguridade e as comunicacións cuánticas. Tamén fai poucas semanas, veíades na prensa, estábamos aquí tamén pois para contalo co reitor e co conselleiro, esa primeira liña de comunicacións cuánticas que se tendía desde o Centro de Supercomputación de Galicia en Santiago hasta aquí a Vigo, Vigo Quantum Communication Center, 120 kilómetros, se non lembro mal, a máis longa de España e, unha das máis longas ata onde sabemos tamén no contexto europeo. É dicir, estánse marcando fitos ao abrigo deste plan complementario moi relevantes e queda feito un traballo de base, quedan uns equipamentos, queda un talento investigador xa captado que é tremendamente relevante e que estou segura que, ademais desto que estamos contando así un pouco nesta benvida, hoxe ides ter a oportunidade que os equipos que traballaron en todo isto durante estes anos vos conten polo miúdo cales son todos os resultados que levan acadados e, onde estamos con todo isto. Dende a Xunta de Galicia, pola nosa banda, identificamos dentro do Plan Galego de Investigación e Innovación que se lanzou este ano e que vai para 3 anos, como sabedes, pois as Deep Tech, en concreto a cuántica dentro desas tecnoloxías, como unha desas liñas de alto impacto que de forma transversal pois que queremos apoiar e así o estaremos e o seguiremos apoiando a través pois do que está marcado nese plan, do que xa se leva posto en marcha a través do Polo de Tecnoloxías Cuánticas de Galicia, da rede, de todo o ecosistema, os instrumentos que se están poñendo pois a vosa disposición para que poidades continuar este bo traballo que xa tedes arrancado, poidedes aproveitar esos equipamentos que estades empregando e queda moito por facer porque agora que xa está esa base creada, pois agora toca probar, toca experimentar, toca seguir mantendo esa posición e incrementando pois ese talento investigador e esas colaboracións. Nada máis, desexarvos que teñades unha xornada pois tremendamente, que estou segura que vai ser tremendamente interesante e nada, os meus parabéns a todos os participantes e aos impulsores tamén destes plans complementarios, en particular do traballo que se fixo neste plan complementario de comunicacións cuánticas aquí dende Galicia. Moitas gracias.
Grazas. Ten a palabra agora Jesús María Salvador Sánchez, como decía, representando ao Ministerio.
Bueno, buenos días a todos. Es un placer estar aquí en Vigo, rodeado de tanta masa crítica, ¿no? Yo, me presentan como representante del Ministerio, pero yo sepáis que soy científico, no de vuestro área de investigación, del área de biomedicina. Pero vamos, que empatizo bastante bien con vosotros porque llevo la misma vida que llevamos todos los científicos, ¿no? Y quiero dar las gracias a Marcos por la amable invitación, al rector de la Universidad de Vigo, a todos los representantes académicos y también de las empresas que también me consta que han participado y colaboran en este empeño, ¿no? Y y sobre todo a vosotros, ¿no? Los científicos que realmente sois los protagonistas de este evento, ¿no? Yo creo que hoy es un día importante para celebrar. Todos tenemos una gran curiosidad, yo el primero, por ver los resultados, ¿no? Por ver los resultados en este campo, en el sentido, como el objetivo de vuestro trabajo, ¿no? De intentar implementar las tecnologías digitales cuánticas, ¿no? Y sobre todo en el tema de ciberseguridad, y hemos tenido la suerte de poder ver las instalaciones, ¿no? Esta mañana, y la verdad es que es bastante interesante ver cómo se combina esa parte teórica con esa parte práctica que se ha podido montar en parte gracias a estos planes, ¿no? Vosotros no lo sabréis, pero es muy curioso que el origen de estos planes complementarios coincide casi con el origen de las instalaciones, por lo que he estado hablando con Marcos de cómo se ha ido montando este centro aquí en Vigo, ¿no? Ha sido casi como vidas gemelas, ¿no? Y los planes complementarios se arrancaron en el 2021 y el impulsor fue el Ministerio, en estrecha colaboración con las comunidades autónomas, ¿no? Aquí con Galicia, que yo creo que esta colaboración ha funcionado estupendamente. Y se crearon con esa idea, con la idea de buscar sinergias entre las administraciones públicas, entre los distintos territorios, las distintas comunidades autónomas, con el Ministerio, ¿no? Para de alguna manera alinear también los proyectos de investigación de I+D y los intereses comunes, ¿no? En este sentido. Y la verdad es que fue muy curioso como, bueno, ahora ya que han pasado 4 años desde aquel momento cuando se originó este plan y se ha visto la evolución y ahora estamos aquí para valorar y ver un poco qué ha pasado, ¿no? Con esa inversión que se ha hecho por parte de las comunidades autónomas, por parte del Ministerio y como habéis aprovechado con tanto talento, seguro que muy bien, esa inversión, pues yo creo que es un buen momento de hacer balance, ¿no? Yo os puedo decir desde el Ministerio que el balance es tremendamente positivo. O sea, ya os lo adelanto, ¿no? La impresión que tenemos desde el Ministerio, y también me consta, he hablado con algunos consejeros de comunidades autónomas, luego escucharemos también al rector de aquí de Vigo a ver qué impresión tiene. Y es una pena, creo que no ha podido venir el consejero, vendrá luego a la clausura del evento, ¿no? Y me gustaría también saber su opinión, pero la impresión que tenemos desde el Ministerio es que ha sido un rotundo éxito este programa complementario, ¿no? Y esto, la verdad es que al final fue diseñado por un par de personas dentro del Ministerio que se fijaron en un modelo europeo en el que vieron que la cogobernanza, la cofinanciación implicaba más los intereses comunes de los territorios y a nivel nacional y que era un buen modelo a explorar, ¿no? Y era un buen modelo a financiar. Y yo creo que el tiempo les ha dado la razón, ¿no? Y gracias a eso pues estamos hoy todos aquí. Yo creo que este plan ha tenido éxito y lo voy a reducir a 4 palabras, ¿no? que definen un poco el éxito que ha tenido. Una ha sido la financiación, otra ha sido la colaboración, otra la coordinación y también creo que el liderazgo, ¿no? La financiación, pues habéis visto que ha sido bastante generosa dentro del estándar español, ¿vale? Porque también comentábamos antes que en otros países, pues bueno, tienen otras posibilidades, incluso esta financiación les hubiese parecido pequeña, pero dentro del estándar español, fijaros que la financiación de estos planes complementarios han sido 466 millones de euros, ¿no? 300 millones de euros por parte de la Administración, por parte del Ministerio, ¿no? Que venían de fondos europeos, y 166 millones de euros entre las 17 comunidades autónomas. Pues creo que es bueno señalar que todas las comunidades autónomas españolas han participado y se han beneficiado de estos programas, ¿no? Y bueno, dentro de eso, las cifras, por ejemplo, aquí en Galicia, yo creo que son bastante importantes. En Galicia se ha beneficiado de una inversión de 45 millones de euros, ¿no? De los que 26 han venido del Ministerio y 19 han venido por parte de... Sí, perdón. Galicia es que ha participado entre todos los planes complementarios, me refiero, en 45 millones de euros, de los que 26 han venido del Ministerio a través del PRTR y 19 de la propia comunidad autónoma. Y solo en comunicación cuántica la inversión global han sido 57 millones de euros, ¿no? 37 del PRTR y 20 también autonómicos. Y concretamente aquí, en lo que es la comunicación cuántica, en la parte gallega, pues han sido casi 10 millones de euros, ¿no? 9,6 millones de euros de inversión, ¿no? Igual, en más o menos el mismo porcentaje, el 60-40 entre el Ministerio y la comunidad autónoma, ¿no? Y estos datos, convendréis conmigo, que son muy significativos dentro del estándar español, porque para que os hagáis una idea, es como la mitad del presupuesto de la Agencia Estatal de Investigación Española, ¿no? Que es la principal financiadora de los proyectos de investigación del Plan Nacional de España, ¿no? Es decir, que prácticamente tiene el doble de presupuesto simplemente que estos planes complementarios, ¿no? Y la Agencia Estatal financia casi 3.000 y pico proyectos cada año, ¿no? O sea que yo creo que eso pone en valor la inversión. Luego os decía también la colaboración. Creo que estos proyectos han creado una herramienta de política científica nueva que realmente ha permitido una colaboración dentro de los investigadores a nivel intraautonómico, pero también interterritorial, ¿no? Como sabéis, porque colaboráis con investigadores de diferentes comunidades autónomas. Y no solo eso, yo creo que ha permitido establecer un diálogo entre el Ministerio y las comunidades autónomas que ha sido bastante próspero a la hora de elaborar este proyecto o este plan de una manera diferente a como existía anteriormente. Y también creo que ha potenciado mucho la colaboración público-privada, porque se están estableciendo muchas sinergias con empresas privadas que han colaborado y se han integrado dentro de estos planes. Se han hecho numerosos convenios, colaboraciones, contratos, y yo creo que eso también es algo bastante importante, porque sabemos dentro de la ciencia española que el nivel de inversión de las empresas privadas en investigación, en I+D, todavía está lejos de lo que sería óptimo, ¿no? Y en eso, desde el Ministerio, os adelanto que estamos haciendo un esfuerzo bastante grande, ¿no? Y desde la Secretaría de Estado hay un interés especial en ir involucrando poco a poco cada vez más a las empresas privadas, ¿no? En inversión en ciencia, tecnología y en innovación. La tercera palabra que os comentaba un poco es la coordinación, ¿no? Creo que todos sabemos lo difícil que ha sido llegar hasta aquí, porque ha habido un montón. Ha habido problemas de índole administrativo, porque, claro, fijaros la complejidad que tienen estos planes. Participan las 17 comunidades autónomas españolas, participa el Ministerio, y hay más de 300 entidades ejecutoras diferentes, cada una con una normativa, con una reglamentación. Entonces, es complicado poner todo ese mecanismo en marcha, que el engranaje funcione, y además a la primera, porque es la primera vez que se ha hecho. Entonces, era un tema bastante arriesgado, por decirlo así. Y yo creo que hay que reconocer que la coordinación que ha habido entre el Ministerio y las comunidades autónomas pues ha permitido crear una serie de sinergias que yo creo que van a aumentar la eficacia de las políticas públicas. También ha permitido alinear pues, recursos autonómicos, recursos locales y recursos nacionales, incluso europeos, ¿no? en una misma línea de investigación. Y eso creo que también, de alguna manera, optimiza los recursos, ¿no? que son limitados en nuestro país. También yo creo que ha permitido hacer una cosa interesante, que es armonizar los intereses de los investigadores básicos, ¿no? Porque gran parte de los investigadores que estáis aquí hacéis investigación básica. Y poco a poco estamos haciendo ese camino hacia la transferencia del conocimiento, ¿no? Pero yo creo que sí que se ha armonizado un poco esos intereses y esa colaboración entre el investigador que hace solo ciencia básica y las empresas y las industrias privadas, ¿no? Industrias que poco a poco se van metiendo en este tema, ¿no? Y eso ha creado, la verdad, es que un ecosistema bastante curioso, ¿no? Un ecosistema singular que yo creo que ha venido para quedarse. Y me gustaría pensar que es así, porque creo que va a ser útil tanto para los investigadores básicos como para las empresas. Y bueno, finalmente el liderazgo, ¿no? Os comentaba, cuando se hicieron estos planes complementarios, pues pensar que primero alguien ha tenido que tener la visión estratégica de diseñar el plan. Luego pensar que hay que tener el liderazgo para ponerlo en marcha, sabiendo las complicaciones que esto tiene con las connotaciones que hay aquí en España a nivel territorial, ¿no? Y luego yo creo que se ha hecho una apuesta realmente valiente, atrevida y bastante generosa a nivel financiero. Y creo que eso es bueno reconocerlo, porque este dinero, pues mucha gente dirá, bueno, dinero que viene de la Unión Europea y tal y cual. Pero es cierto que este dinero, y lo hemos comentado muchas veces en el gabinete, se podía haber utilizado en muchas otras cosas. Y ha sido una decisión estratégica y política el decidir el 40% de estos fondos que venían de la Unión Europea se han utilizado en innovación, en ciencia, en tecnología. Y se podrían haber dedicado en cualquier otra cosa. Y os digo más, muy probablemente se hubiesen utilizado en otras cosas en otro momento en España, ¿no? Pero eso creo que es bueno que lo reconozcamos también. Fijaros, yo creo que el talento, y aquí hablo ya como científico también, el talento en España nunca ha faltado, siempre ha existido talento. Somos un país de mucho talento, pero lo que no tenemos tristemente son los recursos financieros para que ese talento se desarrolle y se potencie, como existe en otros, cuando nos comparamos con los estándares de otros países de la Unión Europea o cuando cruzamos el charco, ¿no? De Estados Unidos. Y yo creo que este tipo de herramientas, este tipo de planes, sí que demuestran que ha habido un cierto compromiso, si me lo permitís, de intentar cambiar el modelo de país, de intentar realmente creernos que a través de la ciencia, la innovación y la tecnología, pues podemos considerar que son motores de bienestar social. Podemos creérnoslo, y yo creo que si nos lo creemos los científicos, si nos lo creemos los gestores públicos, de hecho podemos cambiar ese modelo, o podemos empezar ese tránsito a cambiar el modelo en España. Los logros de los planes complementarios yo creo que han sido bastante llamativos, ¿no? En números, yo estoy deseando escuchar los resultados vuestros en este plan de comunicación cuántica. Pero sí, a nivel general, y para que tengáis una idea muy global y muy reducida, ¿no? Comparando con otros planes complementarios, pues este programa ha permitido la generación de nuevas líneas estratégicas de investigación, que no hubiesen sido financiadas, como os decía, por otras agencias, ¿no? Financiadoras. Ha permitido la financiación de proyectos tecnológicos que van a mejorar las capacidades estratégicas a nivel territorial y a nivel nacional. Ha permitido la contratación, y ya os daré algunos números, de centenares de doctores, tecnólogos, jóvenes investigadores. ha permitido la creación de nuevas infraestructuras tecnológicas, como la que hemos tenido la fortuna de ver esta mañana aquí en Vigo, que han venido para quedarse, porque estas infraestructuras luego podrán ser utilizadas no solo por los científicos que han montado la infraestructura, sino también por otros científicos españoles que se podrán beneficiar del uso de este tipo de infraestructuras. Y también yo creo que se ha conseguido un desarrollo de tecnología que también ha venido para quedarse y que perdurará incluso más allá de cuando estos planes complementarios continúen o no en el futuro. Ya iremos viendo. Y para que tengáis algunos datos globales del impacto que están teniendo estos planes complementarios a nivel nacional, pues os doy algunos datos. Por ejemplo, han participado 337 entidades ejecutoras diferentes. Se han puesto en marcha más de 1000 proyectos. Se han contratado más de 2000 personas. Se han publicado, yo creo que pasaremos de los 2000 artículos próximamente. Todas estas cifras van avanzando. Se han solicitado más de 35 patentes y estos datos ya son antiguos de meses atrás, ¿vale? Se han hecho más de 200 acciones de transferencia, más de 20 acuerdos de explotación con empresas, hubs de innovación, creación de spin-off a lo largo de todo el territorio nacional. Yo creo que los datos son verdaderamente relevantes y seguro que van a tener un impacto en el fortalecimiento de las capacidades tecnológicas del territorio, de aquí de Galicia y de nuestro país. Estamos convencidos. Y ya, bueno, me encantaría finalizar dando la buena noticia de que estos planes complementarios van a continuar, ¿no? Y sería el bombazo, ¿no?, poderlo decir. Tampoco me correspondería a mí decirlo. Pero, bueno, sabéis, todos sois conscientes de las dificultades de la aprobación de los presupuestos generales del Estado, ¿no?, y cómo estamos en un estado de incertidumbre un poco continuo. Sí quiero daros la esperanza de que tenemos muy claro en el Ministerio y en el Gabinete que es muy importante que haya una continuidad, al menos de la estructura del plan complementario, mientras existe la posibilidad de volverlo a financiar como merece esta convocatoria, ¿no? Y vamos a pelear, y en eso tendemos la mano a las comunidades autónomas, ¿no? Y es una pena, bueno, si luego tengo la oportunidad de hablar con el consejero, pues le lanzaré un poco el guante, ¿no? Tenemos la idea, o nos gustaría que las comunidades autónomas sigan teniendo un papel protagonista en esta continuidad de los planes complementarios y al menos en la continuidad de esta estructura para que evite que se pierdan estas sinergias, ¿no?, que se han creado tan estupendas entre vosotros, entre investigadores de toda Galicia y con investigadores de otras comunidades autónomas, ¿no? Nos encantaría poder seguir manteniendo vivo esto mientras realmente podemos volverlo a financiar como esto se merece, ¿no? Y bueno, pues también creo, y bueno, no lo voy a adelantar yo, creo que el secretario de Estado lo dirá próximamente, creo que va a haber buenas noticias. Sabéis que hay en marcha la idea de montar un plan complementario de transferencia, se va a poner en marcha creo que muy pronto, pero bueno, esperemos que os den más detalles las personas que tienen que darlos, ¿no? Pero os anticipo, creo que buenas noticias, os espero. Y solo quería ya despedirme, pero bueno, no quería hacerlo sin volveros a dar las gracias, ¿no?, a los científicos, que ya os digo que para mí creo que sois los grandes protagonistas de este evento, ¿no? Gracias, pues, por poner a Galicia y por poner a España en la élite de la investigación cuántica, ¿no? Gracias por vuestro esfuerzo y por vuestro compromiso. Desde el Ministerio de verdad que trabajamos, y yo como científico, no con ninguna otra intención, con la idea de que los recursos lleguen a los científicos para que la gente pueda ejecutar los fondos y pueda llevar a cabo su proyecto, ¿no? Por cierto, en eso también os tengo que dar la enhorabuena en Galicia, se lo comentaba antes a Marcos, ¿no? A mí que me tocó hacer el informe de ejecución del plan complementario a mitad del camino, Galicia iba en la zona alta de ejecución. O sea, habéis ejecutado muy bien los fondos, cosa que me congratula porque es señal de que el dinero os ha llegado y os lo habéis gastado correctamente. Y Galicia ya el año pasado iba por un nivel de ejecución del 70 y tantos %. Me consta que vais a llegar prácticamente al 100%, si no lo habéis hecho, pero la cosa va a ir bien. Y el año pasado, a nivel nacional, la media de ejecución era el 45%, ¿no? Y vosotros ya estabais por encima del 72, 74%. O sea que muy bien, ¿no? Enhorabuena, porque eso también es señal de que habéis sabido llevar el dinero a los centros ejecutores y les ha llegado a los científicos y los científicos lo han empleado, ¿no? Y me consta que correctamente. Y bueno, ya no me quiero enrollar, me estoy enrollando quizá demasiado. Solo ya lo último que os quiero decir. Yo creo que Bueno, reconocer una cosa también. ¿Sabéis las dificultades que ha habido a nivel administrativo? Y me consta, yo creo que alguno de vosotros sabe lo que es el programa Coffee, aplicaciones como que todos amamos, incluidos en el ministerio. En fin, pero todos sabéis que, claro, a la hora de gestionar los fondos públicos es muy importante que utilicemos herramientas que permitan precisamente eso, que los fondos se utilicen correctamente y que haya un control de gestión de esos fondos, ¿no? Y aunque no nos guste a veces las aplicaciones que nos complican la vida, especialmente a los gestores y a los científicos, yo creo que es bueno reconocer también el trabajo de gestión que han hecho las comunidades autónomas, porque me consta que algunas han tenido incluso que contratar personal especializado para la gestión de este tipo de planes, porque es un poco compleja, y les ha supuesto un esfuerzo adicional, ¿no? Y yo creo que eso también es bueno que los científicos lo sepamos, ¿no? Que a veces ese tipo de cosas pues no las valoramos. Y solo ya, como mensaje final, deciros una cosa. Yo creo que independientemente de la continuidad que esperemos que siga adelante, este programa ya deja un legado. Este programa del Plan Complementario de Comunicación Cuántica deja un legado, ¿no? Como el resto de programas, ¿no? Porque yo creo que se ha creado una red de colaboración interterritorial que eso va a perdurar, eso se va a mantener. Y yo creo que se ha creado un ecosistema de talento y de comunicación con empresas que creo que también ha venido para quedarse. Y si todos, no sé, yo creo que ahora tenemos todos un reto muy apasionante en ese sentido. Y si nos ponemos las pilas y trabajamos duro y aprovechamos este ecosistema que se ha formado, yo creo que realmente sí puede ser uno de los motores que impulse la economía territorial, aquí en Galicia y en España, en el territorio nacional. Y bueno, esperemos que sea así. Ya perdonadme, no me enrollo mucho más. Muchas gracias a todos por vuestra atención.
Marcos, cuando queiras.
Hola, buenos días a todos. Bueno, es un placer estar aquí. Muchas de las cuestiones que quería resaltar hoy pues ya se han mencionado. Entonces, simplemente a lo mejor me quería quedar con 3 aspectos. Por una parte, me gustaría agradecer la implicación tanto del Ministerio como de la Xunta de Galicia y en particular de GAIN por creer en los planes complementarios. Coincido plenamente en lo que nos ha dicho Jesús del Ministerio. Han supuesto un antes y un después. Sobre todo, han sido planes complementarios en 8 áreas diferentes, pero si nos centramos en comunicaciones cuánticas, nos han permitido posicionar a Galicia en un lugar en el que no estábamos y después de muchísimo trabajo, pero sobre todo después de la posibilidad de estos planes, ¿no? Y coincido plenamente en creer que invertir en investigación, invertir en innovación, invertir en talento es una forma de mejorar nuestra sociedad y de crear riqueza. Entonces, no puedo estar más de acuerdo con lo que se ha dicho hoy. Y, desde luego, como digo, han sido fundamental en el caso de las comunicaciones cuánticas para llevarnos al lugar que ahora ocupamos en Galicia y, sobre todo, también para fortalecer nuestras relaciones con los demás miembros de la comunidad nacional y también de la comunidad internacional. Relaciones que ya existían y que estos planes nos han permitido pues, fortalecer todavía mucho más. Y ya no solo a nivel nacional, pero también a nivel gallego, ¿no? Pues hemos conseguido, pues estos planes nos han impulsado para intentar vertebrar mejor cuál es la investigación que hacemos en tecnologías cuánticas en Galicia y en potenciar mucho más nuestras colaboraciones internas. Entonces, ayer, cuando estaba preparando alguna de las presentaciones para hoy, estaba un poco pues, reflexionando y recopilando la información de todo lo que se ha logrado en estos 4 años. Y la verdad es que cuando empezamos, en 2022, pues todas las personas involucradas en las instituciones pues teníamos muchísima ilusión en llevar esto a buen término, pero creo que se han superado todas las expectativas. Y lo digo porque viendo los números, en el plan inicial había unos números que eran los que se había comprometido, pero los hemos superado con creces en varios órdenes de magnitud, ¿no? Y sobre todo en Galicia y en España, pero ya que estamos hoy hablando aquí en Galicia de los planes complementarios en la parte gallega, teníamos talento en tecnologías cuánticas, ¿no? Pero nos faltaba posiblemente infraestructuras y los planes complementarios nos han permitido precisamente cubrir ese hueco o ese déficit que teníamos y que es fundamental para hacer investigación de excelencia y a nivel internacional poder competir con cualquier otro centro. Entonces, viendo los números, pues en Galicia se han dotado varios laboratorios con equipamiento en estado del arte para tecnologías en comunicaciones cuánticas que, como digo, pueden competir con cualquier otro laboratorio internacional, tanto para comunicaciones cuánticas por fibra, por espacio libre y vía satélite, para certificación y hackeo, etcétera. se han dotado todas las infraestructuras que van a redundar en el beneficio de nuestro sistema investigador. Por ejemplo, hace unos días, que se mencionó ya aquí, pues se inauguró esa línea en Galicia, la primera línea en comunicaciones cuánticas. Más allá de su importancia y relevancia, que ya se ha resaltado, hay otro aspecto, sobre todo a nivel investigador. Tenemos ahora acceso a un testbed que nuestros investigadores van a poder utilizar para probar las tecnologías que se desarrollan aquí en Galicia, y que también nos van a facilitar pues, esa labor de desarrollo tecnológico y de investigación. Y, por otra parte, bueno, pues aquí en la Universidad de Vigo, pues próximamente se va a poner una estación óptica terrena, que debería ser en las próximas 2 semanas, que nos va a permitir, con un telescopio de más de 80 centímetros, que nos va a permitir pues, conectarnos a las principales misiones internacionales de comunicaciones cuánticas, incluidas las misiones de la ESA, como por ejemplo Sesga o Eagle One. Y es una infraestructura pionera en España, de los primeros que vamos a tener acceso a esa infraestructura, y hay otras iniciativas también a nivel nacional, en Barcelona y en Madrid, que van a hacer lo mismo próximamente. Y ha sido de nuevo gracias a los planes complementarios. Luego, producción científica. Pues viendo los números, pues el otro día contando, pues hemos producido cerca de 70 artículos en revistas de alto índice de impacto en estas tecnologías. Se han solicitado licencias de software. Hay muchas colaboraciones con empresas. Un aspecto a lo mejor también de los más reseñables o de los que creo que nos podemos sentir más orgullosos es el esfuerzo en atracción de talento. Se ha conseguido atraer muchísimo talento joven, con muchísimas ganas y muchísima fuerza, y también muchísimo talento más contrastado y más senior que nos permiten dar ese salto de calidad para lograr esa excelencia a nivel de investigación. Y tenemos que estar orgullosos de haber conseguido todo ese talento, muchos de ellos está aquí en la sala, que hayan decidido apostar por Galicia y que hayan venido aquí. Y por último, me gustaría mencionar también que estas inversiones, cuando se quiere apostar por algo, obviamente hay que invertir, y si las cosas van bien, que creo que es el caso, pues normalmente se necesita invertir todavía más. Y esta inversión ya está dando sus frutos y dará todavía más frutos a medio y largo plazo. Y frutos lo estamos viendo de nuevo. Ayer, contando, por ejemplo, iniciativas, nos ha permitido a la comunidad gallega y a la comunidad nacional pues, posicionarse mucho mejor para acudir a convocatorias de financiación pública, europeas, nacionales, internacionales, y viendo simplemente el esfuerzo que se ha hecho en Galicia en estos 4 años y ver los proyectos en los que las distintas instituciones gallegas están involucradas, pues en este momento el retorno está siendo más de 10 millones de euros. Y esperamos que eso, obviamente, todavía aumente mucho más en el futuro. O sea, que ha sido una inversión que ya estamos viendo un retorno y que debería dar mucho más retorno a medio y largo plazo. Y me gustaría concluir con una pequeña reivindicación. Y esa reivindicación es doble. Por una parte, se ha hecho un esfuerzo enorme por atraer talento. Y aquí tenemos el talento, pues necesitamos que ese esfuerzo y que programas de atracción de talento continúen. Sé que el Ministerio hace un esfuerzo muy grande con programas como Atrae, pero que ese esfuerzo se mantenga y se intensifique. Y necesitamos luego, sobre todo, políticas de retención de talento. Una vez que hemos conseguido que ese talento venga aquí, necesitamos conservarlo. Tenemos ahora el talento, tenemos las infraestructuras, pues lo que necesitamos ahora es tener medidas que nos permitan retener ese talento en Galicia. Entonces, es una pequeña reivindicación. Y una segunda reivindicación es también que, obviamente, después de haber hecho todo este esfuerzo y de ponernos en una situación en la que ahora podemos competir a nivel internacional con cualquier otra institución, necesitamos que ese apoyo continúe. No podemos quedarnos aquí, después de todo el esfuerzo logrado, sino que necesitamos que ese apoyo continúe. Y ahora que tenemos las infraestructuras y el talento, necesitamos que, por una parte, se haga un esfuerzo para extender en la medida posible estos planes complementarios que han demostrado ser un instrumento de mucho éxito. Y necesitamos también que el Gobierno gallego, como hasta ahora, nos siga apoyando para que podamos seguir posicionando a Galicia como referente en el ámbito de las tecnologías cuánticas. Y sin mucho más, agradecer a todos de nuevo la presencia y espero que disfrutemos mucho de la jornada de hoy. Gracias.
Moi ben, como estamos moi fora de tempo, vou a ser case telegráfico. Os que me coñecedes xa sabedes que non se me dá nada ben. Entón, eu só quero decir un par de cousas. A primeira é que estamos aquí para gañar o futuro. Gañar o futuro significa construir unha sociedade baseada no coñecemento. E temos os vimbios, temos as ferramentas, temos o talento, temos o esforzo, Temos tamén a visión, porque estes planes complementarios son unha mostra de que hai visión de futuro, e temos a situación, unha situación que hai 20 ou 30 anos era impensable, ¿no? Para min, que levo na universidade dos anos 80, creo que neste momento podemos presumir de moitas cousas. En Galicia, por non falar de toda España, podemos presumir de ter un sistema universitario galego público, totalmente público, de alta calidade. As 3 universidades que conforman este sistema están a ser quen de extraer o talento que hai na nosa comunidade, incluso xente que ven de fora, de pulilo, de poñelo a disposición da sociedade, e o estamos facendo moi ben. Pero temos, ademais, un magnífico ecosistema, ¿no? Dentro das universidades se fixo un esforzo para que haxa centros de investigación de calidade. A rede de centros CIGUS creo que é unha realidade magnífica. Nos temos, nos temas dos que estamos a falar, xa citaba antes AtlanTTic, que forma parte de esta iniciativa de Comunicaciones Cuánticas, de algún xeito tamén está dentro de AtlanTTic, pero tamén en Coruña e tamén en Santiago temos situacións semellantes, ¿no? Temos o Cesga, que está, ademais, a traballar con todas as universidades galegas, está a facer un traballo a nivel de toda Galicia. Temos centros tecnolóxicos. Podo citar, por exemplo, que vexo aquí a Gradia, ¿no? Que é un centro tecnolóxico de telecomunicacións que surdiu da Universidade de Vigo e que o está a facer moi ben, ¿no? E penso que neste momento temos por primeira vez na historia da nosa comunidade autónoma a posibilidade de sacar a cabeza e de ser pioneiros e de ser dos que tiran do tren e non dos que ven pasar os trens. Eu creo que neste momento, se sigue contabilizando esa colaboración público-privada e esa colaboración entre institucións, pareceme magnífico que estean colaborando o Ministerio, o Goberno de España e o Goberno Autonómico. Creo que ese é o reto fundamental que temos que ter en riba da mesa e que temos que aproveitar para facer esa achega ao futuro. Creo que estamos nunha situación na que Galicia pódese convertir, Galicia, España e Europa pódense convertir en cabeza da investigación que se leva a cabo nesas tecnologías que van a marcar o futuro. Falamos de comunicacións cuánticas, falamos de computación cuántica, falamos de inteligencia artificial, todas estas novas tecnologías que están chegando e que temos o talento aquí, temos que, efectivamente, como moi ben decía Marcos Curty, impedir que se marche, porque aquí atopan un sitio onde realizar ben o seu traballo. A pregunta que facía Marcos Curty, aproveito que son o último en falar, que a Comunidade Autónoma vai a poñer en marcha este ano un programa de retención, de atracción de talento extraordinario, que creo que ademais aos 3 niveles que vai a traballar vai a funcionar para poñer esas pezas que precisamos para ser cabeza de león e non ser cola de ratón. E desde logo a última cousa que me queda por decir é que precisamos que este apoio, que Europa siga crendo en si mesma. Eu creo que a resposta para que podamos funcionar Europa, eu creo que no seu día, cando chegou a pandemia, Europa púxose as pilas. Creo que eu estaba moi orgulloso, ¿no?, de sentirme europeo, de ver que Europa estaba creendo en si mesma e que ia apostar a través dos fondos de recuperación polo coñecemento xerado a nivel europeo. Espero que eso non esmoreza, que non se perda. Dende logo pidolle tanto ao Goberno de España como ao Goberno de Galicia que fagan todo o posible para que siga habendo ese apoio, e dende logo creo que co que se fixo, que creo que a avaliación vai a ser moi positiva, creo que estamos na liña de poder competir con calquera país avanzado dos que estamos acostumados a mirar con envexa. Eu espero que dentro de, si seguimos con este esforzo compartido, dentro de 10, dentro de 15, dentro de 20 anos, moitos pensen que Europa é o líder nestas novas tecnologías. Desexo vos o mellor para estas xornadas e por suposto que fagades moito máis por traballar conxuntamente. Sempre o digo, vivimos nun país pequeno, no noso caso de Galicia, ademais aquí nun curruncho, e sempre o digo, xuntos somos máis fortes, todos xuntos podemos. Así que, moitísimas grazas e parabéns polo vosso labor. Grazas.
invite a speaker that is Professor Marco Luca Marini from the University of York. That he's going to give the invite talk. Let me say, I know Marcos for more than 20 years. He has been very well known for his research, first at Toshiba, where he has been spent many years, and now, as I said, in a few years at the University of York. During his 20-something years working on quantum communication, he has made tremendous contributions to the field. And he's very well known for many of them. But if I could highlight one, it's the protocol twin field. That is a protocol that was put forward in 2018. And it's a protocol that it was really incredible because suddenly allowed us to increase the distance, essentially to double the distance. And actually the recent experiments that have the world record distance are due to this protocol. They have achieved 1,000 kilometers without relying on satellites. And this is thanks to Marco and to the team of Toshiba. And to the team of Toshiba. So anyway, give him an applause and thanks for your talk.
Okay. Buenos días a todos. Estoy muy contento de estar aquí en Vigo. Muchas gracias, Marcos, por la introducción and la invitación. And I'm afraid my Spanish is quite limited, so I should go back to English, even though it's limited as well, but, you know, less limited. So, indeed, I was asked to give a brief overview of quantum communications technologies. So I came up with this title, Business Case and Challenges Ahead. So I will run through the slides. I already know, perhaps I will hurry up a little bit, but this is just to give a general overview of the field in preparation of the technical preparations that will, presentations that will follow. So I hope that will make it. Right, so I don't think I need to explain that quantum technologies can overcome some tasks that conventional information technology can't. And this is a very famous example of having one photon, ultraviolet, down converted into 2 infrared photons. And this is at the heart of so many applications in quantum technologies, from quantum computing, quantum communications, and indeed has become with photons here in the corner, so this little visible region of the entire electromagnetic spectrum. And this has become a little bit the symbol of so many experiments related to quantum technologies. And even they adopted, the IOP adopted it for the Quantum Week, which is this week, indeed. I don't know if you knew it. I only found out while preparing this talk. IOP decided that this is the week of quantum, so we are very happy to have this event exactly in this week. And this is related to the spectrum that is coming out of this crystal, even though this is a famous artifact from Austrian group by Anton Zeilinger. And we also happen to be in the year of quantum, so International Year of Quantum Science and Technology. And this was called by the United Nations, to celebrate 100 years from the formulation of quantum mechanics. So indeed, is a special moment to be in quantum technologies or quantum information science and technologies. And we have indeed very many initiatives around. So I would like to start introducing the field from the situation in the UK, which is the one I'm more familiar with. And recently we had the National Quantum Strategy just put forward by the DCIT, the Ministry of Science, Innovation and Technology. That was March 2023. But actually, the situation in the UK started much earlier, back in 2014. And the UK was one of the pioneers, from a country-wise point of view, to start this technology by preparing 4 quantum research hubs in quantum communications, quantum sensing, computing, and imaging. These were the first 4 quantum hubs put forward from a country. And then in each of these fields, you can find somehow a quantum advantage. In some of the fields, it's clearer. For example, in quantum communications, there is a clear quantum advantage. In the other fields, there is expectation of very big quantum advantages, even though if it is a little bit more tricky to demonstrate that. However, these are kind of 4 pillars that then were followed by many other countries and also expanded by the UK, Europe, and worldwide. And this was very successful as a strategy because indeed it brought the UK to be one of the world leader countries in quantum technologies. And, but not only for that, also to relate to what has been just said, it is an engine to create business and to stimulate economy. So there is indeed now a thriving business community in the UK, which is second only to the US in terms of quantum companies created around quantum technologies. And there is also a high level of private investment. So this is a map to show more or less the investment from industry in relation to quantum technologies. Clearly there is a lion part in the area of London, but there is also kind of considerable investments in Sweden, Wales, and other regions of the country. So overall, you can create a community and you can create an industry with that, so you can have really a return of investment, which is very useful to have, of course. And indeed, this stimulated additional funding in the UK because last year, the DCIT decided to put another 2.5 billion pounds in 10 years into the program, which is very good news. So this was the first year of the second phase, actually third phase of the quantum research hubs. And in this case, we have now 5 different hubs that are similar to the initial 4, but we have one for PNT, position, navigation, and timing, one around biomed, which is entirely new, led by UCL in London and University of Cambridge. And then we have sensing, imaging, and timing, still in Birmingham, and in Oxford, still quantum computation hub, which was confirmed. But for this conference, the most important one and relevant is this, which is around quantum communications. So this is now called integrated quantum networks. And as it was said, now networks are kind of prominent. So rather than point-to-point link with QKD, everybody is looking into expanded networks, pretty much as it happens for internet or for optical networks that are already deployed all over the world. Clearly, the Europe is active in this field, very active, and I think we will have presentations on this, so I don't aim to be exhaustive on this front. I will just mention the quantum flagship, of course, which was launched back in 2018, even though agreements were there since 2016. So in a similar time as the UK moved, also Europe moved. The budget is consistent, about 1 billion euro in 10 years. And it brings together many stakeholders So there was a ramp-up phase that finished in 2021. There is a new phase with more funding and more projects. And the two really relevant projects for quantum communications were these two, OpenQKD and the EuroQCI, which really paved the way to what is coming now. Clearly, there is a bigger effort worldwide, and this slide that actually you can find on the internet is an attempt to summarize these efforts. I am not sure how reliable it is. It seems a little bit conservative to me. However, it comes from McKinsey & Company, and I thought it could be kind of reliable. However, worldwide, we have a total of about $38 billion investment. The investment is led by China, which is the country that invested the most, but we also have big investment from South Korea, Europe, the UK, and a little bit the US, even though they are somehow behind and unexpectedly low in budget. However, this is projected to increase to this level by 2040, and this is why I think it is a little bit of a conservative estimate, because I've read much more positive estimates somewhere else. However, it's best to be conservative and still show some growth in the field. So this is in general about the quantum technology, which, as I said, is composed of several pillars like communications, computation, simulations, etc. However, we want to focus a little bit on communications here. So just to give a little bit of background on what quantum communication is, what is the core business of quantum communication. I would say it is generation of high-quality random numbers and quantum coherence at distance. So we can generate these high-quality random numbers either locally, so we can generate a string of these numbers with a good confidence that these are truly random. And this is not as trivial as it sounds, because clearly everyone can generate random numbers, or at least that look random, but they are not, because they are generated via a classical process that can be predicted or can be repeated in time. So genuine random numbers are difficult to generate, and you can use quantum mechanics to do that. But even more impressive, you can generate random strings at distance and correlated in an exact manner, in a way that these strings are only known to Alice and Bob and are unknown to any third party. So this is something that was known to be possible, really, until the 70s or 80s. So this is a true quantum advantage that we have in the field, is undeniable. You cannot achieve either of these two tasks with classical means only. This is not only science fiction. We have demonstrations of random number generation as fast as 100 gigabit per second, which is quite impressive, and also of, let's say, generation of these strings that we can use as cryptographic keys at distance that have reached now 100 megabit per second in a fiber of 10 kilometers, and as Marcos said, can now go even beyond 1,000 kilometers in optical fibers with an experiment done in this paper. So generation of true random numbers is possible via a physical process that we trust, being quantum mechanical in essence, like this one. You have photons that are particles that can only be detected either here or there, cannot be detected in two places. And so this is a truly random process, and you can exploit this to generate zeros and ones. It's not the most efficient process, but it's the easiest to visualize, possibly. There are quantum random number generators already on the market, and you can purchase from various suppliers. And they are actually already working at the certification of randomness, for example, at NIST and ISO. So it's a very advanced technique. And equally, the QKD, quantum key distribution, so distributing these two strings at distance in a secret way, is also very well advanced. And these are just some examples, perhaps even a little bit outdated, of suppliers selling QKD systems. This is the one in York. We are not selling it, but I just want to put it there. These are the typical figures you can achieve, more or less 100 kilometers in optical fiber and 1 megabit per second at 50 kilometers of optical fiber, figures for commercial devices. And then you can also see many more tools, as we have seen in the visit at the labs earlier on this morning. You have bulk optics devices, you have deformable mirrors, wavefront sensors to control the turbulence. You have telescopes like this. This is the twin telescope we have at York at the moment, 65 centimeters aperture each telescope. This is a single photon detector based on superconducting nanowires. This is the same nonlinear crystal I showed at the beginning, and this is a compact version of a source like this, where you can basically take the entangled photons out of these two ports and just play with that. And this is also a useful tool called White Rabbit time synchronization that you can use to synchronize big networks, including quantum networks. So this is just to say that the technology is not only cybersecurity, but is also photonics, is also optics, and is also optoelectronics. So it's basically a big market of stakeholders are there. So why do we want to use this technology for? What would we want to use this technology for? Well, indeed, this is something I already mentioned. You have two parties, typically Alice and Bob, they want to communicate securely, and someone in the middle wants to spy. This is usually called Eve. How do we guarantee that this communication is secure? Well, they have tried many solutions in physics and mathematics. This is an historical problem that goes back even 2,000–3,000 years. The current solution is the one to combine software and hardware, so mathematics and physics. On the software side, you have algorithms like the ones belonging to the so-called post-quantum cryptography. And on the right side, you have physics and optoelectronic devices, but also algorithms. So this part is not entirely physical. Of course, there is a big theory part behind this. And the idea is to combine the two and use them to guarantee a better encryption that nowadays we call quantum safe cryptography, because this is a cryptography that is safe also against the most powerful quantum computer or the most powerful computer that can come in the future. In my view, this is more interesting because if I can use somehow the same sentence from Landauer, who was a physicist back in the 70s, he said that information is physical. I mean, in the end, when you have to encode information and use information, you must use voltages, currents, or levels of lights. So in the end, you have to carry this information and process this information. That is the basic level of information, which is physical. And I would say it's exactly the same. At the end, security or secrecy is physical. It is very easy to hack an algorithm when this algorithm is implemented in a CPU, and perhaps you can probe the CPU in some way. You will break AES or any other form of algorithm very easily. There is a device that is sold on the internet. It's called Chip Whisperer. Probably you know that. And with this device, you can break any AES advanced encryption standard that is actually the standard used in US military army, so kind of a serious one. This is just to say that in the end, security and information are physical, so it makes sense to study a physical system to guarantee the security of an infrastructure. So what is the base of security? I think we all know that, but it's good to go through it. It's the no-cloning theorem. You encode some bits that you want to ideally transmit as a key into quantum states. Then these quantum states are transmitted over to the other party, which decodes them as bits, hopefully the same bits that were transmitted. It is impossible for anyone intercepting these bits to create exact clones or copies of these unknown states. And essentially this is called as no-cloning theorem and prevents, in principle, attacks from anyone in the middle. Clearly, classically, this is different, and indeed, it should be noted that we have at this level, a classical level, this is the information that you want to encode, maybe in your phase modulator or in your intensity modulator. So up to here, the information is classical. When you encode that into quantum particles, it becomes quantum, and at that point is unhackable, is unbreakable, is absolutely secure, provably secure. However, between classical and quantum, there is a perimeter somehow. There is a line that I didn't draw here, but there must be a line between classical and quantum, which defines somehow the security perimeter. Because when you go back to classical, then this string of bits can be copied, can be broadcast, can be cloned, or whatever you want. So essentially, it is impossible to guarantee security when it is classical at this level. It is only possible to guarantee it when it is at this quantum level. And our job is somehow to push this quantum boundary more and more into the classical world so that we can extend the security in this way, and ideally we can have one day just quantum systems playing around between them and distributing quantum keys, and we can only use the minimum of it that we need as classical systems. Clearly the field has a big history. This is a slide courtesy of Fei Hushu. Started back in '84, we are around 2023, so we can't go through this history, but definitely it had several milestones that some people in this audience also contributed to, like decoy states or first security proofs or first attack to implementation security. And in fact, in all this big field, I would like to identify a couple of challenges that are specific to this quantum communication field. The first one is really implementation security. We can say it started more or less around here with this PNS attack in 2000, and then it developed into security proofs and then solutions to security proofs, following the security proofs and then other experiments. So this has been mentioned. You have to guarantee security of a physical system. I will say a word about that. And the second challenge is this one, which is about distance. So clearly, we are working mainly with photons. Photons are scattered or absorbed. You cannot go forever, and we cannot really use optical amplifiers because of the no-cloning theorem. So QKD has a limitation in distance, and this is the second challenge we want to overcome, ideally. So about the first challenge, QKD implementation security, let's just say that it is difficult to implement the no-cloning theorem exactly in practice. In practice, you want to have a single photon state, but actually in practice you have an attenuated laser like this, and you go from this level of photons to 1, but you only obtain 1 with a certain probability. You can obtain 0, 2, 3 photons in a certain pulse. So the situation is actually more similar to this. You have a certain number of photons in each pulse rather than an exact quantum state. And then you also have imperfect detectors. So when you reach at the end, you have some losses in your detector. And this can be exploited by the intermediate attacker to perform a very powerful attack that is indeed called photon number splitting attack, PNS attack. And this was one of the first attacks pointed out against the implementation of the no-cloning theorem, which is QKD, not against the theory and the principle. So clearly this is kind of difficult to deal with, but let me say that it has been completely resolved. You have now the theory that includes this source, and you also have the decoy state that actually use this source to perform a very good QKD implementation. And actually this source now became the best possible source you can use in QKD because they are fast and efficient. However, in reality, you have complex systems, and while this channel can be entirely untrusted, and this is the beauty of QKD because you don't have to worry about Eve at all, you have to trust these two local sort of equipment that you have. And to trust them, you have to calibrate them carefully, or you have to remove some trust by inventing some clever protocols. So this is essentially the heart of the research in this field, and Marcos and Vadim and Hugo and many others have contributed significantly to this field. And the second challenge is the distance. So clearly, if you propagate photons in free space, you have this kind of scaling because you have the photon expanding like on a sphere. If you propagate them in fiber, then the photon is more confined, but you have scattering and absorption, so you have actually an exponential decrease of the transmittance. Clearly, this is a big problem, and when you go to networks, how can you repeat this signal from one point to another, and dealing with this challenge here of absorption? The typical solution is the one of using trusted nodes. So essentially, you distill a key that goes from Alice to this Bob, then Alice and Bob here distill a new key that goes to the second Bob, and then again, and so forth until you reach the final end. So a new key is distributed here, there, and there. And this is actually very effective because you can achieve any distance in this way, even though there are some counterindications somehow. But this has been so efficient that actually in China, for example, they used this method to distribute keys in a network that is about 10,000 kilometers long. This is the latest estimate, between fibers and satellite. So it's a very complex and big network. And you can see here all the nodes with all the rates. So this is really happening. You know, it's not science fiction. It's something that is already deployed. And clearly there are many more networks, even here in Spain, in Madrid, and in other countries, USA, South Korea, UK, etc. And worldwide, we have several attempts at network in Japan, South Korea, Europe. So these are all the initiatives around quantum networks that we have worldwide. And in Europe, we have in particular, I wanted to mention these three projects. Everything started back in 2008 with the project called SECO-QC in Vienna, where many companies were joining efforts to create this initial network of 5 points. I was there, unfortunately for me, witnessing this initial network. It was very exciting at the time. And then after some time, this was taken again with this other project, OpenQKD, also led by the Austrian Institute of Technology, because they were also the ones behind this. And this was clearly much bigger and much richer in the budget, and this paved the way for EUQCI, which we are all familiar with. 27 EU member states. Unfortunately, the UK is not one of these members. This is such a regret, but what can you do? And then it was kicked off in 2023, terrestrial and space segments, and we are expecting the first European quantum satellite, Eagle-1, in 2025 or 2026. And clearly there is behind a big vision, and this is the basis of a quantum internet in Europe. In the UK in particular, we are now aiming to overcome this architecture of trusted nodes. Somehow we want to create something that contains untrusted nodes, and I'll show you some reason for that. However, essentially using entanglement, quantum memories, or single photon sources, you can try and turn a trusted node into an untrusted node. And in some cases, they are even easier to build, actually. So it could be advantageous to have that. But it is greatly believed that if you want to have a big quantum internet also connecting quantum computers, you must have quantum coherence and entanglement between the nodes. So that's why we're looking a little bit in that direction. And so coming back to this slide, yes, trusted nodes are great. However, they have their own problems. The security must be checked at every node, of course, because in this node, the key will become classical and can be copied and transmitted somewhere else. Then the end users perhaps don't trust the trusted node because maybe the end users are Microsoft and the trusted node are IBM's, and they don't trust each other because they are competitors, right? And also, the trusted node is perfectly fine for terrestrial link, but other links are kind of challenging. For example, what if you have to put a trusted node here in the middle of the Irish Sea? So this is a transmission we tried and actually succeeded in the UK, between UK and Ireland, zone of Manchester and area of Dublin. So ideally, you would put a quantum, a trusted node here to repeat the key there and there, but it's not an easy task. And I think this is also interesting for Galicia, because Galicia is around here, and in the area of Bilbao, more or less, I think here, or Santander, you have these big transoceanic fibers. One is Marea, is very recent, very new, and one of the best connecting Europe to the US. And how can you transmit a signal from here to there? You need a lot of trusted nodes in between. So why don't we start thinking of submarine trusted nodes that we can put there, or some untrusted nodes, just to repeat the signal across a transoceanic fiber? I think this is a very interesting challenge. However, current solutions are essentially three. So one is satellite communications. With satellite, clearly you can go up to the satellite, have a satellite communicating with another, and then back to the ground. So you can cover big distances, even intercontinental distances. These are two examples of the only two quantum satellites we have so far. This is the famous Meteus satellites from USTC in China, and this is a more recent Jinan-1 microsatellite that still comes from China. Hopefully, very soon we will have other satellites from Europe and the UK. The second solution is quantum repeaters. You have to repeat the quantum signal over and over across all these untrusted nodes now using entanglement. It is notoriously difficult to do that. Someone believes that it's even more difficult to create a quantum repeater than a quantum computer, because you have to do the same operation of a quantum computer over a distance of maybe 20 kilometers. So it could be very challenging to build that, but we have to be clever and think out of the box. Maybe there are solutions around that. This is an attempt in that direction. I already mentioned twin field QKD. It has been called an effective quantum repeater because actually it overcomes the threshold, the secret key capacity threshold of a repeaterless QKD protocol, even though it's not repeatable itself. So you cannot repeat twin field QKD like a standard quantum repeater. So that's why it's effective only. It's not a full-fledged quantum repeater, but still useful to overcome considerable distance like this, 1,000 kilometers in optical fibers. And finally, specialty fibers and materials in general. I think is very impressive the progress that, for example, these hollow core fibers have done recently. They managed to go below the barrier of silica fibers, so 0.091 dB per kilometer is much lower than the standard 0.2 dB per kilometer that they have. And actually their projections are very good, that they think they can reach 0.02 dB per kilometers, which can bring us directly to cover 10,000 kilometers or 8,000 kilometers in this kind of hollow core fiber. So this is just to say that overall there are many activities going around quantum communications. These are just a few examples. I've mentioned some quantum protocols, I've shown some quantum devices, and we have shown some quantum networks. Standardization is also very important. You have to standardize the technology if you want the industry to adopt this technology and to have interoperability between different vendors. So this is a very hot topic. And of course, chip integration. You don't want to have a QKD system that is as big as a room when you want to deploy something. So typically we work with racks, but the idea is also to make them smaller and smaller until we can have them of the size of a mobile phone and use it like that. So here are my conclusions. Most importantly, I think that security in the end is physical, it's not just algorithmic. So classical cryptography can be broken in a physical way, whereas QKD leveraged the laws of physics to protect security and in a long term with something that is close to IT secure, so close to information theoretic security. The algorithm itself is IT secure, then the implementation, I think, is close to IT. Quantum communication is becoming infrastructure, and I think this is now the base for the future quantum internet, as everybody is saying. What is more important is that, indeed, quantum technologies in general and quantum communications are growth engines that can generate income and can generate industry and employments. And also, the UK and Europe are both leading in this field. So this is a unique chance to become leaders in this field and actually to guide the rest of the efforts worldwide. So I think in general, overall, in the next 5-10 years, we will define standards, infrastructures, and also leader of the future quantum internet. Thank you for your attention.
Thank you, Marco, for the very nice talk. I was wondering if there is any question that we want to take the opportunity to ask Marco. Any question in the audience? People seem to be a bit shy. So let me break the ice just with some aspects that you didn't mention. What is the status of certification in UK regarding with quantum communication? Do you know?
Yes, essentially the UK is present in ETSI, mainly in ETSI there is a QKD industry specification group that is led by Martin Ward, he is Toshiba. So that is essentially the main engine of standardization. ETSI was a European institute, now is an international institute like ISO, ITU. And the idea in that case is to prepare a so-called protection profile, which is essentially a container where you can put all your implementation security problems with the best solutions that we know. And also we indicate how to perform the right measurements to decide what is the security risk and what is the security solution, essentially. So that is, for example, the Trojan horse attack already appears as a standard in this kind of protection profile, as an example, but then we can have many more examples. Then it is present via BSI in other committees like ISO, ITUT, etc. But I think in these other standardization bodies, the effort is coming more from Asia rather than from Europe, as far as I know.
There is no kind of Nostradamus project at the UK?
Not that I'm aware, no.
Here's another question.
Hi. You mentioned right at the end the hollow core fibers and the surprising, the really amazing development that has happened there. And I know a lot of that is research is happening in Southampton. Have you guys had the chance to try, quantum communications over hollow core?
Yes, we have written to Francesco Poletti just last week and received a clear no. But we will keep writing. And now, essentially, he wears two hats because he's with the University of Southampton, but also with Microsoft, because their spin-off has been acquired by Microsoft. And so now, basically, it's Microsoft's hollow core fibers. What he thinks is that next year it will be much easier for him to collaborate with groups around, because now they are still in the development of extending the distance of their short hollow core fiber, So that's what they're doing now.
Thanks.
Any other question? If not, over there.
Okay, thank you very much for your interesting talk. A brief question. When you talk about the submarine optical QKD between Europe, for instance, and America, how many trust nodes are necessary?
It's a good question, really. And I don't know. I think the typical distance they have between optical repeaters, because actually in the transoceanic fiber there, they use optical repeaters. So there is no chance that a light sent here can reach the other end after 6,000 kilometers. It's impossible. So they have so many optical amplifiers, and they also have 15,000 volts going down together next to the fiber to give energy to the amplifiers, indeed. So I don't know exactly how many they have there, but in my opinion, it is reasonable to assume that they have at least one every 100 kilometers to have a comfortable repetition of the signal. Perhaps they can push it farther to 200 kilometers, but I think after 200 kilometers, the signal is kind of degraded from what I know. So you can think of 6,000 kilometers covered with optical amplifiers every 100 kilometers. I think the situation would be very similar with trusted nodes.
Okay, so maybe one last question, one curiosity. I never asked you about this, but it's just about twin field, because twin field has been a fantastic breakthrough in the field, no? And now that with our understanding, after 7 years, we know essentially just thinking in single photon interference is very easy to see, and coming even from the repeater previous results, but you went through this idea in a different way, coming from phase encoding MDI QKD. So if you could just clarify how was your idea behind twin field, and whether you really expected this improvement on the execute rate, this change of the scaling, or it came as a surprise. So if you can just in a couple of minutes, particularly since there are here so many young people, you can elaborate how was this process to come to this protocol.
Yes, indeed. There was this paper by Tamaki and colleagues back in 2012 where they were demonstrating this phase-based MDI QKD, and I was really surprised by the modest values that they have for their key rate and also the distance. They can barely reach 5-10 kilometers, you know, with all the optimizations and everything. And so starting thinking about that, we, Gillian and myself, start discussing this. And then at some point, we really came up with kind of a similar idea, but for QKD, where you take the standard Toshiba setup, essentially, and you split it in two. And you think that the photon doesn't come from the single transmitter, but from two different transmitters. And then you immediately see that you can double the distance. So for me, that was not very intuitive, but for Gillian was kind of immediately clear. So he pushed me in that direction, and we eventually came up with this. But I think the main element was to take the phase-based MDI QKD and embed in it the decoy state technique. And even in the first security proof that we came up with Kiyoshi, we devised this code mode and test mode. In the test mode, you only do decoy states without revealing the phase, and then in the code mode, you reveal everything like in phase-based MDI QKD. The decoy state was really the trick to give the extra scaling to the protocol.
Thank you. So let's thank Marco again for the very nice talk. And now we are coming to start presenting some of the results that has been achieved during the Planes Complementarios. We will start with Cesga.
Vale, sí, si quieres ponlo, pero...
Y después cuando quieras cambiar, cambiamos.
Vale. Marcos.
Hi, everybody. Sorry, Marcos, should I continue in English or Spanish, English? What is the... Okay, let's go. Okay, it's fine. Okay, so hi everybody. My name is David Barral. I'm the local project coordinator of the PCCC project at Cesga. And here with me is Iago Fernandez Jobo, that is my colleague. And I'm going to present you the results of our research center related to the PCCC project. So this is the people that has contributed to this, and I'm going to go through it fast because we don't have too much time. So Cesga working two axes of the project. One is towards EuroQCI, that our main goal it was to deploy a link between Cesga and Vigo Quantum Communication Center. And the second one was to develop software for quantum computing. So I'm going to give you some numbers about our link between Cesga and Vigo Quantum Communication Center. We have Alice and Bob, that are QLXR systems from QTI. This was obtained through Fujitsu in a public tender. It's European technology, and the protocol is a 3-state BB84 encoded in time beam. So apart from that, from this tender, we got two external SNSPDs that allow us to go even further or having an increased secret key rate. And we have two dark fibers between the two centers. This was got by the company Lintia. No connectors, no amplifiers. And we can use that. Apart from using the link, we can do some experiments with that. So the design length is 123 kilometers. The design loss budget is 28 dB. And at this moment, we are a bit above that loss budget. And with that, using the SNSPDs, we have a key rate of 3.6 kilobits per second. This was working, this is the mean value, it was working by 1 month without any interruption. In the lab, before going to the real link, we check, and with internal detectors, with attenuation of 30 dB, we have around 70 bits per second. And with 40 dB attenuation, that with standard fiber would be equivalent to around 200 kilometers, we have 576 bits per second. Okay, and with the link, we also developed two use cases. One was with Gradient, and it was and with our partners from AtlanTTic, the University of País Basque, and the Polytechnic University of Madrid. That it was a software for securization of a 5G core network. It was like let's say in a 5G network, the part that goes in fiber. And we are currently working in a transnational testbed using QKD links, and where we don't have QKD links, we use post-quantum cryptography to make like a big national, let's say, QKD network. And the second one was with ITG. We developed a software for key management of multi-step QKD networks with trusted nodes. So this is a software where you have a network, and you can connect every two, let's say, partners of the network, like using trusted node and jumping, XORing the secret key, the key from one partner to the other. And this was with, again, with AtlanTTic and Tecnalia as partners. At the end of my talk, we are going to make a demo showing the use of this software, and well, you will see what we are going to do, and the QKD link between Cesga and Vigo Quantum Communication Center. And just to say that this softwares will be available in our webpage soon. Okay, in the second axis that we work is software for quantum computing. And as you know, at Cesga we have a quantum computer, so we are very interested in developing this kind of software. The long-range view of Cesga about quantum computing is like that we will have some kind of data center or farms with quantum computers connected in a quantum network where we will perform what we call high-performance quantum computing, where we will have like a parallel computing with an hybrid system between classical and quantum computers, and with the quantum computers in a distributed system. So this led us to like our first goal in the project. It was to review the field of distributed quantum computing, and we together with the group of Tomás Pena at Citius, we wrote a review that gives you like information about the different layers that you need to develop in a distributed quantum computing system. Just to say that this review in 1 year has around 100 sites, so we know that it's a hot topic, this stuff. So in the group, we are 5 people that was hired in this, and the different people works in different projects or work together. One of them is to use to make distributed variational quantum agent solvers with so kind of simulations of variational quantum agent solvers with different noise profiles. So this, for example, is a simulation in our cluster in Finisterrae using a software developed by another group in Cesga that is paid by Quantum Spain, that is called Cunca. And with this, we could input different noise profiles in the system and check how, with different noises, the distributed quantum computing performed. Another work in the group was like to check in a distributed quantum computing how to make non-local operations. As we know that entanglement swapping is not optimal for some of these operations. So what we found is like some of these operations are better, or in terms of resources are more efficient when you make some of them in one of the quantum computers. So if you have few quantum computers, you could use them to make the non-local operations and the others for the rest. So just to say that, sorry. So we have posters upstairs of every of these works. So if you want to know more, you go there and you can ask. So another work is we are carrying out is about quantum recurrent neural networks. That is another kind of variational algorithm for time series prediction. Also, apart from distributed quantum computing, we make digital annealing and digital quantum computing to apply it to food industry and drug discovery. This is basically to use this in quantum chemistry. So Mariam was working mainly in this field, and she used this kind of optimization algorithms to, for instance, evaluate the generation of freshness in the beer, and also to develop antibiotics. So I invite you to go and talk with her. She will explain. Also, we have experience in photonic quantum computing, and there is a part of the typical gate-based quantum computer. We have another frameworks of quantum computing that is, for example, measurement-based quantum computing. This is well adapted to photonics. We have developed like some architectures to generate cluster states that are necessary for this kind of quantum computing. And also, we are studying universal programmable photonic circuits that you need to, for example, if you want to simulate the evolution of a quantum system, you need a unitary matrix And you can do that in photonics using this kind of mass tender interferometers. But there are other devices that make them, and we prove the universality of these devices and what are the optimal parameters. In this axis, we also work with 3 companies in use cases. One was with Mestre Lab Research, simulating nuclear magnetic resonance spectra with a quantum computer. Another one with Bahia Software, that it was using distributed quantum computing for accelerating the execution of some circuits. And with MEDUs, to, again, kind of quantum chemistry, using classical simulations for this kind of simulations of peptide folding. Apart from the 2 axes that are like research axis, we also participate in the axis 6, that is about human resources and formation, innovation, and entrepreneurship. So we had, we organized some courses with Digigal and Train, if I remember, Train on Tech, on transfer and innovation, project management, innovation transfer, intangible assets, creativity in transfer, and communication in transfer. This was very interesting, and we learned a lot. And just finally, I would like to give you some numbers about the participation of Cesga in the project. So we were 5 postdoc level people. We published 11 papers, 5 are now in review. We have few in preparation, and we have software that we are going to license. We participate in different conferences and gave seminars. We also participate in the Bachelor of Science thesis, in 7 Bachelor of Science theses, 4 master degree theses, and we have 3 PhD students now in the group. And what I consider very important for us is like we got a few projects that are related to quantum during the project. So this means that this can continue what we did at PC3 in the project. This is Iberian QCI, that is a QKD project, QEX, Graviteca, Deep Quantum, Catalyze, and the IA Factory that has a part about quantum computing. And also, some of us, we got some fellowships, like a postdoctoral research fellowship from Xunta Galicia, one Ramon y Cajal fellowship, and contract with companies, with Estrella Galicia. So this is the people that made this possible. And with this, I would thanks your attention for this part, but, but now we are going to make a small demonstration of the software. And the demonstration, basically, we are going to use the QKD link between Cesga and Vigo to produce some keys between the 2 sites. And here we are going to control a small rover that is at Cesga using a VPN link. So this VPN link has a standard security, but on top of it, we are going to put a pre-shared symmetric key. And this pre-shared symmetric key is going to be key generated by the QKD devices at Santiago. But since we don't have QKD in the Wi-Fi part, here we are going to use post-quantum cryptography. So the software we developed at ITG is going to make this. Here we are using this for this particular case, but this software can do it with any network. Where in the part that you don't have QKD, it simulates the QKD link with post-quantum cryptography, with Kyber. So maybe, Jago, we can try to connect the computer. And we have our colleague Juan is at Cesga. So So this is the control. Jago is going to control the device. Here we are at Cesga. This is our Bob. This is our QKD system. This is Bob. This is the SNSPDs, the single photon detectors we have here. So now the rover is moving. Maybe you can go a bit on the right. Okay. So here you can see better here is the SNSPDs and the QKD system. Well, the quality is not very good, but you can see the different fibers with the classical and the quantum channel. Yeah, well, maybe. So now we are going to go through the Cesga's. We are going to see the finished array. That is our HPC system. This control, and this feed of video have the security, the standard security layer, but has another security layer using the QKD keys. So here you have the finished array or HPC system and the different parts. This is finished array, if I remember, 3. And here you have finished array 2. It's around here. I don't know what is this, but whatever. Yeah, maybe you can go. And we are going to pass by Finisterra and show you Cumio that is at the end of this corridor. And at the end, just to show you that this is real, we will try to show you the rover moving with the reflection in a mirror. So this is an example that you could use this kind of QKD system for surveillance. Well, this is again the finished array. We try to not go through this part because sometimes the camera falls down and we don't see anything. So Cumio is over there. Still, maybe you don't see it. Well, the connection is not. What? We're having problems with latency. There is a bit of latency problem. Yeah. I came yesterday to check the latency of the. So, well, here you have the. So this is because the problem of latency of the signal, it's difficult to control the.
This is purely classical problem.
Yeah, classical problem, not quantum. Yeah, just to finish, we would like to show you, but at least you could see well the image of the rover moving on the. And here you have the quantum computer, Cumio, with the FPGAs and the cryogenic part. And so, yeah, that's it. This is what we wanted to show you.
Thank you, Davide, for the nice presentation, and it was nice to meet the rover that you have in Cesga. So we are really running out of time, so if there is any quick question, this is the time. If not, my suggestion is that we move forward to the last talk before the break, and then during the break, of course, you can address a bit about any questions you have about the work that has been done in Cesga. Okay, so thank him again. And now we go to the last session before the lunch break about the work done in University of Coruña. Lo tienen ahí. No tienes que poner IBM. Sí. De todas formas, ahora hay otras iniciativas también en España. Están ahí Cesga. Yo creo que para que no sé cuál es el estado, pero le puedes contar a David o a cualquier
Bien, hola, buenos días. Mi nombre es Francisco Novoa y él es David Soler y formamos parte del equipo de UDC con el Centro de Investigación CITIC y con el Centro de Investigación de AtlanTTic de UVigo. Y bueno, vaya papelón. Después de la charla de David con el rover en tiempo real y de la de Marco, y además justo antes de la hora de la comida, bueno, pues intentaré ser lo más breve y conciso posible. Y bueno, nosotros hemos organizado esta charla en dos partes. Una primera que simplemente pretende mostrar los resultados que hemos alcanzado en el desarrollo de nuestro trabajo, y luego pues una parte más técnica que además está complementada con una demostración que tenemos en la parte de arriba. Para nuestra demostración y nuestra investigación todo el equipamiento cabe en una cajita y lo hemos traído y lo tenemos ahí puesto en la mesa. Y además tenemos un póster también para terminar de explicar el funcionamiento. Para que tengáis un poco el contexto de cuál ha sido la dimensión de nuestro grupo de trabajo, pues además de David y de mí mismo, pues había colaborado pues una persona que ha estado contratada durante año y medio en el proyecto, y otro investigador senior, que es Carlos Dafonte, y aquí en AtlanTTic, pues Ana y Manuel. Los fondos de los que hemos dispuesto para nuestra investigación es de unos 100.000 euros. Y bueno, pues el objetivo de nuestro trabajo era desarrollar casos de uso. Y los casos de uso que hemos desarrollado pues han sido un servicio de entropía en el que intentamos proporcionar a los usuarios finales acceso a QRNGs. Este proyecto, este caso de uso lo hemos complementado después, integrándolo con un servicio de mensajería grupal basado en MLS, reforzado con el uso de claves cuánticas. Este es el caso de uso que os va a detallar David ahora en un momentito, y además es el caso de uso que está disponible también para que podáis ver cómo funciona en la demostración que tenemos en la parte de arriba. La estructura básica en la que entrará David ahora a contaros es la que podéis ver aquí. La idea es que, bueno, pues, desplegar una infraestructura en la que un usuario final pueda acceder, pues, utilizando un teléfono móvil a claves QRNG, y además, pues, de este modo, pues, que se puedan utilizar para pues, aplicaciones diversas que requieran algún tipo de seguridad reforzada. Además, otra de las aportaciones que tenemos en este trabajo es la posibilidad de que este servicio funcione con un tipo de autenticación anónima, de modo que no queden vinculadas por las identidades de los usuarios con las claves que han sido asignadas. El sistema de mensajería, pues, es una extensión de este trabajo, donde, bueno, pues lo que pretendemos es reforzar el comportamiento del protocolo MLS para la gestión de grupos de mensajería, pues integrándolo con el Entropy as a Service que definimos en el primer caso de uso. Bien, finalizando la parte de resultados obtenidos, bueno, pues conforme a nuestra financiación modesta, los resultados son un poco más modestos. Hemos publicado un par de artículos JCR en revistas Q1 y Q2. Hay un par de publicaciones que están ahí todavía en proceso de revisión, pero que confiamos en que salgan finalmente. Y además, pues bueno, pues hemos participado en diferentes congresos y jornadas, pues a lo largo de estos 3 últimos años. Finalmente, para no robarle tiempo a David, que es el protagonista de todo esto, pues indicaros que uno de nuestros mayores éxitos es el talento investigador captado, que es el propio David, que comenzó como personal contratado con cargo a esta financiación y bueno, pues pasó a ser después becario predoctoral de la Xunta y ahora mismo pues tiene una plaza de profesor a tiempo muy parcial y muy precaria en la UDC, pero de momento seguimos contando con él para que presente su tesis doctoral en este ámbito de conocimiento en el año que viene. Y por mi parte, nada más. Muchas gracias a Marcos y a todos los grupos de trabajo por habernos dado la oportunidad de participar en este plan. Y nada, pues ya os dejo con David para que os dé los detalles técnicos del caso de uso.
Vale, bueno, muchas gracias. Yo voy a detallar un poco más la parte técnica del proyecto que hemos realizado. Bueno, también por complementar un poco lo que comentó Fran, también a raíz del proyecto hemos dirigido 2 proyectos de fin de grado y otros 2 de fin de máster, alguno de ellos pendiente de su entrega pronto ya. Vale, pues como decíamos, el enfoque de nuestro proyecto era el desarrollo de una serie de casos de uso para las comunicaciones cuánticas y, por lo tanto, nuestro enfoque ha sido pues, encontrar las herramientas que mejor se integren con todas las tecnologías de comunicación que ya existan actualmente. De todas las tecnologías cuánticas, la que hemos identificado como más interesante para su aplicación directa son los generadores cuánticos de números aleatorios o QRNG que bueno, generan claves con entropía pues, superior a los generados por los generadores utilizados ampliamente. Además, bueno, para demostrar la aplicabilidad de esta tecnología, aparte del desarrollo de la arquitectura para la distribución de claves cuánticas, hemos desarrollado una aplicación móvil que las integra dentro de un servicio de mensajería, pues porque consideramos que es lo que los usuarios están más familiarizados, ¿no? Las aplicaciones de mensajería son de las formas de comunicación más utilizadas en Internet, por lo tanto consideramos que reforzarlas con seguridad cuántica pues, podría ser una manera interesante de demostrar pues, las ventajas de las tecnologías cuánticas. Voy a omitir de momento la parte de la aplicación de mensajería y me voy a centrar en esta arquitectura que hemos desarrollado, que es la de Entropy as a Service, precisamente para la distribución de las claves cuánticas. Bueno, estos QRNGs generan claves de alta entropía, pero desafortunadamente en la actualidad tienen un precio bastante elevado y por lo tanto no es posible pues, distribuir uno a cada usuario, ¿no? Imaginamos que estos QRNGs solo estarán disponibles pues en centros de investigación o instituciones bancarias que pues, tengan un nivel de seguridad superior. Por lo tanto, lo que nosotros hemos planteado es una arquitectura por la cual cualquier usuario puede solicitar este tipo de claves a un servidor que sí que disponga de un QRNG. Para ello, bueno, también hemos desarrollado un protocolo que es la base de todo esto, que permite que los usuarios soliciten estas claves anónimamente, debido a que, claro, estas claves son material bastante sensible porque luego utilizarán pues para cifrar sus comunicaciones y es necesario que no sea posible asociar la identidad de cada usuario a la clave que ha recibido. Aquí tenemos un poco la arquitectura. Veis que a la derecha está este servicio remoto, que sería la institución esta bancaria o de investigación que mencionaba, con acceso a un QRNG. Además, tendríamos una serie de ramas locales, que podría ser pues, cualquier localización que decidiese proporcionar este servicio de claves generadas por QRNG, que tendría disponible un lector NFC. Los usuarios desde su teléfono móvil podrían acceder a este lector para descargar las claves de QRNG generadas en este servicio remoto. Hemos decidido complementar también esta arquitectura, bueno, planteando la posibilidad de añadir un enlace de QKD entre estas ramas locales y el servicio remoto. Esto es precisamente la parte en la que tenemos una demo después en la sesión de póster. Si queréis pasaros tenemos cada una de las entidades que aparecen aquí, pues la tenemos desplegada en un dispositivo distinto y os puedo comentar un poco más si os interesa. Vale, en cuanto a la aplicación de mensajería, como os decía, hemos buscado cuál sería la aplicación con la que más familiaridad tienen los usuarios para aplicar pues este protocolo de distribución de claves cuánticas y por eso hemos decidido pues, desarrollar una aplicación de mensajería instantánea. En concreto hemos utilizado el protocolo de Messaging Layer Security o MLS, que bueno, es un reciente estándar de grupos de mensajería, está específicamente dedicado a la mensajería en grupo. Y bueno, tiene una serie de ventajas, por ejemplo, la eficiencia en las actualizaciones de miembros del grupo. Como os decía, lo que hemos desarrollado es esta aplicación de mensajería que utiliza las claves obtenidas de la plataforma de EAS para establecer el secreto grupal entre todos los miembros del grupo, ¿no? Para comunicarse de forma privada, todos los miembros necesitan conocer una clave secreta que se deriva pues por una serie de pasos definidos por el protocolo de esta clave obtenida por el EAS. Vale, bueno, también por mencionar, para añadir una capa de seguridad adicional, pues hemos decidido que esta aplicación de mensajería se comunique mediante redes peer-to-peer, es decir, no pase ningún mensaje por un servidor. Así, bueno, tenemos una arquitectura un tanto más privada. Vale, esto sería la visión general de nuestra aplicación de mensajería. Veis que cada teléfono móvil tiene una conexión con el servicio EAS, a través del cual solicitaría periódicamente material de clave generado por el QRNG y además, por otro lado, se comunica con todo el resto de aplicaciones de la red mediante el... ¿Ha pasado algo? ¿Vale? Vale, parece que todo bien. Bueno, se comunica mediante el resto de aplicaciones de la red mediante el protocolo MLS. Una de las ventajas que tiene este protocolo es que, bueno, periódicamente cada miembro del grupo puede generar una actualización que renueva el secreto compartido grupal. Es decir, introduce nueva entropía en el grupo. Y es precisamente esta entropía que se introduce la que se obtiene del servicio de EAS. Es decir, periódicamente se van obteniendo claves de QRNG que mediante el protocolo MLS se introducen en el grupo de mensajería para renovar el secreto común. Vale. Bueno, tenemos aquí unas demostraciones que quizá no tenemos mucho tiempo. Voy a poner una en la cual desde un teléfono móvil obtenemos la entropía. No sé si esto se está reproduciendo. Bueno, si no lo vemos después en la demostración, si os interesa. La idea era simplemente mostraros cómo desde un teléfono móvil conseguimos interactuar con la plataforma de EAS para descargarnos las claves QRNG de forma anónima, es decir, que no se pueda asociar esa clave pues, a la persona que lo ha solicitado. Y bueno, complementamos esta aplicación de mensajería con unas pruebas en las que demostramos bueno, que la carga computacional de la utilización de este protocolo y de nuestra arquitectura de EAS es muy similar a las de otras aplicaciones de mensajería, por lo tanto no supondría un coste adicional por parte del usuario. Y nada, en conclusión, pues en este proyecto hemos conseguido desarrollar un caso de uso para las tecnologías cuánticas, en concreto pues para los generadores cuánticos de números aleatorios y lo hemos integrado de forma lo más transparente posible para el usuario en una aplicación de mensajería de forma que sea sencillo pues, entender cuáles son las ventajas de estas tecnologías. Y eso es todo por nuestra parte. Si tenéis cualquier duda, pues comentadlo.
Muchas gracias por la presentación. No sé si hay alguna cuestión. Si no, yo creo que como estamos tan mal de tiempo, nos vamos ahora a la comida y cualquier cuestión la podéis abordar ahí. También just one thing, because since we are running out of time, so my suggestion, we are going to make the lunch shorter. So we come back around 25 or 22:03. So in about 40, 45 minutes. Okay?
Okay, welcome back from lunch, everyone. I hope you enjoyed it. I know it was a bit short, but you will get another chance to enjoy the catering during the coffee break. And now we will continue with the technical session, and we first have the presentation from the University of Santiago Compostela with the Suso Lineares starting.
¿Cómo va esto? No sé dónde yo di.
Pero echámoslo, ¿no?
Ah, pechas. Para maximizar.
Vale. Ahí. Este. O que pasa que se te separas moito do micrófono, tampouco escoitaremos.
Con eso
de aí hacia para a seguinte e aí para atrás.
Aí para atrás, vale. Este para a seguinte, vale. E despois isto é o punteiro. Vale. Sí. Vale. Hola, good afternoon. Bueno, imos ca presentación de Santiago, un pouco difícil despois do lunch, pero bueno. Vou empezar eu, que son Suso Liñares, do grupo do Laboratorio de Materiales Cuánticos e Fotónica. Continuará Javier Mas, do IFAE, e despois Tomás Fernández, do CITIUS. Bueno, entonces, I'm going to present the activities of the Laboratory of Quantum Materials and Photonics Group from USC. It's more or less it's an experimental part, and then our research line corresponds to the line 2, hardware for quantum communications, and two tasks, QKD, hardware for QKD in optical fibers, and also enabling technologies, integrated devices. Okay, then the primary aim is the development. It means theory, design, fabrication, optical characterization of photonic integrated circuits by ion exchange in glass. It means ion exchange glass chips. And for high-dimensional passive QKD in optical fibers. We use path and polarization optical modes. You can see a general integrated device in the image with synchronic directional couplers and also phase shifters, okay? Well, the question is that the ion exchange in glass is a simple and efficient technology because you can control the fabrication parameters very accurately, very precisely, okay? So it's a technology also, a platform, ion exchange in glass, highly compatible with optical fibers. And finally, it's a low-cost technology, okay? Well, we study three kinds of devices from an experimental point of view. Devices for passive measurements of high-dimensional QKD states, devices for passive generation of high-dimensional QKD states. High-dimensional means 4 or 8, dimension 4 or 8, okay? By using or by photon source, SPDC, spontaneous parametric down conversion, or even by using coherent states. It was a proposal by Marcos Curty, okay? Our primary aim is to use SPDC source, but integrated in the ion exchange glass chips. And finally, a third kind of devices are devices for passive compensation. It means to cancel the optical perturbations in the optical line. It's the plug and play QKD, okay? This is an image of our equipment for fabrication of selective ion exchange in glass. It's optical lithography. We have a deposition chamber, a photoresist spinner, a laser writing, an IonX oven, working around 300 and 500 Celsius degrees. We have a microphotolithography equipment. All this is only for proofs of concept, because our equipment has some limitations, okay? But we can prove if the device is okay or not. Our first contribution was a paper entitled Quantum Projectors Implemented with Optical Directional Couplers in Ion Exchange Glasses. the primary result is that determination of empirical curves to obtain the fabrication parameters of a very wide family of synchronic directional couplers, and so, therefore, of many photonic integrated circuits, such as quantum projectors. A quantum projector is a device to measure quantum states. For instance, you can see, I don't know, oh, sorry. You can see this point up and this point down is a projective measurement, okay? It's a projective measurement in an optical base. In this case, it's the Y base, but we can use another base, but not us, because the circuit can change the base in a random way, okay? And we can measure the QKD states in a random base, optical base. In this circuit, the important thing is the directional couplers, and we need a phase shifter, a phase gate, okay? A phase shifter. But there is another ion chain glass chips like this one that doesn't need phase shifters. This chip implement POVM projective measurements, okay? But there are many other devices, integrated devices, which doesn't need phase shifters. For instance, this is a passive generation of QKD states with SPDC. Our primary aim is to introduce this quantum source inside of our chip. It's an ongoing research project to integrate SPDC source in polarized ion chain glass bipoling. Okay. This is another example of integrated device to generate random QKD states. It's based in a proposal of Marcos Curty, but in this case with path modes, no polarization modes. Okay, we can use multi-core optical fibers, for example, and so on. For instance, we can implement chips for Bell stage measurement, for autocompensation, and so on. But the problem, our problem, was the phase shifters. So we propose these devices to implement phase gates with synchronic directional couplers, in particular abrupt directional couplers. We can see gradual directional couplers and abrupt directional couplers. And these abrupt directional couplers or this other kind of directional couplers can implement phase shifts. And these phase shifters are very robust. It means that small imperfections don't produce large errors. It's very important. These phase shifters are close to topological phase. Okay. This was the second contribution, and this is a quantum projector for dimension 4, when we use Q quartz, okay? And the measure is in a random base, optical base. We need eight paths, okay? And these results can be easily adapted to other platforms. For example, to silicon, which is highly compatible also with optical fibers. The third contribution was a chromatic study of our chips, because the wavelength is a very important parameter in these devices, okay? In particular, we studied the short wavelength band between 700 and 900 nanometers. It can be interesting for QKD in short distance, of course, in optical fibers, or can be very interesting for free space QKD, this chromatic study, okay? And another study, another activities are related with a proposal of a new protocol. It's a variant of the BBM 92 protocol, but the advantage is that it has intrinsic autocompensation. It means that the perturbation of the optical lines are cancelled in a natural way, okay? And it has all advantage of the MDI protocol. These are the 4 contributions in publications. Now we have sent to submission another works. This is an extension of our results to continuous variable. It's very interesting because the optical communication, standard optical communications, has many homodyne detection systems. Then we can use this kind of devices to generate QKD. And finally, another ARKIP work is a hybrid cryptography. It's related to my question to the Professor Marcos Luca Martini, okay? Because the submarine lines are very long, and our proposal is to introduce a hybrid approach. It means that introduce additional physical security layers, of course, classical additional physical security layers, because to insert in the submarine lines several trusty nodes is quite complicated from a technological point of view. And I finish this is a slide about our equipment to characterize our optical devices. Is the optical system working? This is a small image of the chips, glass chips. This is our SPDC source, quantum source. And this is the material which was acquired by the financial support of the Quantum Communications Program. Thank you very much.
So we continue immediately with the second presentation and then maybe have time for questions after that. Or if this takes a while, does someone want to ask a question now? Sure.
Thank you. Question, these optical chips, can you make them polarization independent? Yeah, independent of polarization. I come in with my light in this chip and beam splitters, whatever. This is polarization independent. You can design them. Okay, but not independent of the polarization.
Okay, then we'll continue with the next presentation by Javier Mas.
Okay, so good afternoon. My name is Javier Mas. I belong to the ICFAE, Instituto Galego de Física de Altas Energías. And well, I'll be very brief. So my contribution to this project is quite small. So just to frame the work that we have been doing at the ICFAE, let me start by saying that I am a theoretical physicist working in quantum gravity. So it's something which sounds a bit scary and probably very far apart from this. From the side of what you're interested in, I would frame our work in the context of what's usually called quantum state transfer, which is something similar to quantum state teleportation, which is what you all have learned in standard textbooks, but it's not quite. It's more a kind of teleportation that happens in condensed matter systems instead of photonic systems. Yeah. So essentially, you think you have a lattice or a condensed matter system, a spin system. It has a Hamiltonian, and then you can insert a state, say at the end, and then the Hamiltonian will scramble the whole thing with time. At some moment, you will not recognize what you inserted in, but there's if the thing is correctly chosen, there will be a revival at some moment, and this revival will happen somewhere else. And this is the quantum state transfer. Yeah. So to be more concrete, so you see this circuit here is more or less what I'm what I've been saying. So there's a circuit, and then you insert psi on one end of the circuit. There's something going on in between, and then you recover this psi at the other end of the circuit. The circuit is a proxy for your solid or your condensed matter system. In our case, the kind of condensed matter system we have been working with has a name which probably you have never heard. It's called SYK Hamiltonian. It's a bunch of Majorana fermions. And it has some mysterious relation with the physics of black holes and wormholes. So in essence, this process of inserting the state at one end and recovering at the other end is dual in a sense to what happens when you plunge into a wormhole and you are ejected at the other side of the universe. And there's a way to bring this thing to a more rigorous this statement is to a more rigorous mathematical statement, which goes under the name of the ADS-CFT correspondence. You might have heard of it at some moment. Has something that boils down from string theory, and it proposes that this kind of revival should be seen in a quantum computer. So this is a difficult project. We have not achieved this quantum state transfer, this condensed matter teleportation. There are many groups. Google announced it at some moment, but it's very much cast under doubt. But this project has several steps that you have to fulfill. One of them is creating the initial state. You know, the initial state is sometimes the bottleneck of quantum computing, one of the bottlenecks that is usually ignored. So producing the initial state here is called the thermophile double of this Hamiltonian. It's just a name. It's a state that you can. It's well known in the textbooks. So to produce this state is a difficult thing, and this was the subject of the first part of our research, and then to study the stability of the dual geometry. So this concerning research. Also, I'm involved in other part of the project which has to do with equipment, and in particular, since I'm very much involved in education, and many of you know that I'm the coordinator of the master program. So we bought this equipment here, which is this 1-qubit quantum computer, which is based on NV Center, and this we use in the classes for demonstrations. Is the only, if they want, the only optoatomic setup that we have so far in the master. We hope to have more in the coming future. So, but we use this 1-qubit quantum computer for explaining things at the master, also for outreach. So I've used the money for having 2 PhD persons that have been involved in this research projects I've been talking about. And so we've published a couple of papers that, let me see if this goes or doesn't go. Well, if not, okay, here. So the first one is precisely the one that I commented upon, which is the fact that you have to prepare a state. It's worthwhile stating that this article had a spin-off. We realized after publishing that this method produces automatically the full spectrum of your Hamiltonian, and then we initiated a collaboration with Cesga, with Dani Faeldi, who's sitting there, and Mestre Lab, who are Alexandre, who is sitting upstairs. We initiated a collaboration to try to use this bonus track that this method produced to try to match NMR spectra. So we hope to continue this collaboration in the near future. So the second and third papers are more technical. They if you know the word floquet, has to do with the possibility of exciting periodically a system, periodically in time. So it's the same system, but with a periodic driving. This is more or less what I wanted to say. I think Thomas is coming next. Yeah. If there's any question or...
And we can take one question real quick.
Yeah.
Just one quick question, Javier. When you say preparing the state is the difficulty, is that the state that you're going to teleport or the state that is involved in the implementation of the Hamiltonian?
Is the state you inserted. Imagine you have 0, 0, 0, and you just insert one qubit state in the first qubit, and then you wait. And this pops up at the end. It's the same as teleportation, but it's mediated by a lattice of things. It's not by a photon.
But does that mean that you can only teleport a particular state? So it's not a universal...
No. It's a generic state. I mean, you can insert any.
Okay.
No, it's
all right,
state.
Thanks.
Okay, and then we have the third talk by Tomás Fernández Pena. Go ahead.
Hello, thank you. I'm going to be very brief. I'm going to present the development we carried out in the CITIUS, in the Center of Centro de Investigación en Tecnologías de Información of the USC. I'm going to change completely the subject. Now I'm going to talk, we work in software, and our point of view of the QPUs of quantum computing right now is quite similar to the one of the CITIUS. We think that the QPUs are going to be used like GPUs or FPGAs are used today into a computer system. So we have a classical computer, a classical supercomputer, and we have a quantum processing unit that can be collocated in the same node that the classical one, or distributed around a supercomputer, an IGPC system. So our line started with the study of the state of the art in quantum computing, in general, in distributed quantum computing, and in quantum intermediate languages and quantum compilers. Quantum intermediate languages are used by the compilers to translate, instead of translating directly for high-level languages to the assembler, quantum assembler. Quantum intermediate languages is a middle like this. Middle layer is about here. So the software is translated to these intermediate languages, and from these intermediate languages, another compiler translates to the specific language for the specific QPU. So we start studying the state of the art in quantum computing, distributed QC, and quantum intermediate languages, and we present 2 reviews about these topics. From these topics, we start to work in 3 lines. The first line is developing a new intermediate representation for distributed quantum computing that we call NetQueer. Queer, without the net, is a Microsoft standard. It's quantum intermediate representation developed by Microsoft for quantum computers. So we extend queer. We put the net in front of the Q, so we can use this intermediate representation with a distributed quantum computer. This intermediate representation is based on LLVM, so it's quite general. There are a lot of software supporting it. The second line is the integration of quantum computing as an heterogeneous devices. As I said, we think that the QPUs are going to be used like an accelerator. We have a code writing in a high-level language like C, C++, or Rust, or any one, and we define a kernel that is moved to a GPU or moved to a QPU. So we think that instead of reinventing the wheel, we propose to use the current standard for programming accelerators, and there are 2 standards. The most important one are OpenCL, POCL, and SYCL. This OpenCL is based in C, and SYCL is based in C++. OpenCL, let's say that OpenCL is low level and SYCL is high level. So we propose to extend these classical languages to include QPUs as accelerators. And the last line is the development of the simulator for distributed quantum computers that is called NetQ-MPI. MPI is the standard for programming distributed memory computers, and they are proposed from, I don't remember the name of the authors, I don't remember the name. They are proposed of extending MPI to the quantum realm. So the proposal of QMPI is more theoretical than any other thing. Is only a proposed without implementation. So we propose a real implementation that right now works on simulators. This project, the PC3, allows us to contract one person for 2 years. The person now is working, Jorge is set over there, and now is working at Cesga. Continue in the same line of the distributed quantum computing, but it's not exactly like that. And we have 2 PhD that we hope at least one to be presented next year. At least one. I'm looking for you, yes. I'm looking to you. You have to present it next year. As the results were presented in 5 journals. One is the review of distributed quantum computing that was mentioned before for David at Cesga, what we prepare with people in Cesga, and was published in a very good journal that is 3 of 258 journals, so it's very high impact. The other journal was presented in the Future Generation Computer System was the presentation of NetQueer, that was an extension of Queer for distributed quantum computing. And in the Journal of Supercomputing, we present also a review for the intermediate representation. The InQuasm, that is an Inquire compiler to NetQuasm. NetQuasm is also a low-level programming for distributed quantum computer. And finally, we present the QP integration in OpenShell for heterogeneous programming. This is in journals, and in international conference, we present another survey, this time for quantum compilation process in the Europar 2024 conference. And the NetQMPI and SQL we present 1 month ago in the IEEE clusters in Edinburgh. Also, we make a presentation in the ECA this year. And I think that is all for me, from my part. Yes, this is all.
Does anyone have a question for Thomas?
Okay. I forgot to say that these last 2 posters are we present in the cluster, are presented like poster and are here. So if you want to know more details, you can ask.
Okay, perfect. We'll check that out and ask your questions there. Then thank the 3 speakers again, and we start with the next session. So now we have the technical presentations from the Vigo Quantum Communication Center, starting with Víctor Zapatero.
¿O es esta? ¿Me la mandas?
can send it through the phone. So David, I will push it hours then, right?
Buenas tardes a todos. My name is Víctor Zapatero. I am a senior postdoc in the Quantum Communication Theory group from the Vigo Quantum Communication Center. So I will be talking on behalf of the Quantum Communication Theory group. So we scientists don't like this kind of metrics very much, but this was supposed to be for the politicians who already left, but anyway. So what is the scientific outcome of our group during Planes Complementarios? On the one hand, we have published more than 30 research papers in high-impact journals. We have done contributions to more than 30 international conferences. We have also done research stays in different international institutions, and on top of that, we have licensed the software. We have published 2 review papers. We have attended workshops, contributed with tutorial talks. We have contributed to book chapters, and so on and so forth. Okay. And that's all about bragging. Now let's move to some particular topics which I would like to talk about that we have been working on during these years. Now, the first topic is this very general security framework for quantum key distribution, okay? So what is this? This is formalism to address the security of the original BB84 protocol. And the very appealing thing that this formalism has is that it only relies on, let's say, a very mild characterization of the state preparation, okay? So essentially, what you do need for the application of this framework is you need your states, the ones you prepare, to be close to some, not necessarily ideal, but let's say good performing states, okay? And this is what's represented by that equation that you see there. So there's the part that you want, which is the qubit state, and then some non-qubit state that is a very dangerous thing from the point of view of security. And the weight of this component, which is uncharacterized, the weight of it is what you need to lower bound, okay? And as long as you have something like this, the proof goes through. Now, what have we done? So we can compare, for instance, the performance of this new formalism with existing approaches to address the security of BB84 with arbitrary imperfections. And what we find is that we get a huge advantage compared with existing tools, and this is what you can see on the left graph, okay? And then on the other hand, another thing that you can do is you can try and compare with the best performance you can expect from numerical analysis within the framework, because the formalism provides an analytical secret key formula and a purely analytical analysis. And what we see is that it is essentially tight. So in the asymptotic regime, where you don't have any fine statistics, you just cannot get any better than that, okay? Now, so that is one topic. Of course, there is one downside to this, and it seems, and the downside is that if you remember this undesired non-qubit component, you need a very tight lower bound on it, and you need this bound to be very small, okay? But in fact, this is not a deficiency of the analysis itself, but it's more of a fundamental limitation of prepare and measure quantum key distribution protocols. Okay. What's next? Another topic that we have been working on a lot in this group is pulse correlations. So pulse correlations refer to the fact that there is interdependence in the state preparation in different rounds. This is something that you typically exclude in security proofs, and it can compromise the security, of course. But even if the correlations take place in a degree of freedom which is not the one that you use for the encoding, this already breaks the security, okay? So in this sense, from a theory standpoint, what happens is that the correlations can be seen as a particular kind of side channel that leaks information about the correlated settings, okay? And this is kind of the flavor that all the security proofs that we have to tackle this problem have. This is the common denominator to all of them. So we came up with, let's say, proofs for specific kinds of correlations. Then we collaborated with people from the group of Davide and people from the group of Vadim to kind of characterize or try to test the inputs that you need for the security proof to go through. And we also collaborated with external groups. We collaborated with external groups so we could kind of design countermeasures to mitigate the effect of correlations, okay? And this is something you can see here. I don't want to enter the details, especially given what happened before, but on top, what you can see is the case of phase correlations. This is one of the problems that we tackle, okay? On the left, you see kind of the basics of the security proof, and then on the right, what you see is an experimental setup that we came up with to sort of test the magnitude of the correlations in the phase, okay? And then on the bottom part of the plot, what you have is, on the left, this is a very graphic thing, so this sort of tree plot shows that actually commercial systems do have intensity correlations in them, okay? If they didn't, you would only see a single horizontal line, so the branching means that every new pulse comes with correlations from earlier pulses. And then on the right, what we do is we pick this data, and then with our dedicated proof, we see what the secret key rate you would expect is, okay? Now, and also one last thing that we did is most of these proofs account for the case where you have finite length correlations, and we sort of have a formalism to extend it to the unbounded, to the setting where you have unbounded correlations. Okay, what's next? Passive QKD, this is another thing we've been working on. What's this? This is just about eliminating modulators and eliminating random number generators from your QKD setup. So if you do this you can do, and you can replace with, let's say, a fixed interference, quantum interference mechanism, and this can be your source. And you end up having a much simpler source, probably much cheaper source, and that you can operate at higher frequencies. And on top of that, you get the advantage that since it doesn't have any modulator, it doesn't have modulator-related loopholes, let's say. But it also comes with some limitation of its own, okay? And we did the original proposal of a fully passive QKD source. We participated in the very first experiment demonstrating it. These are some plots from the experiment. We did a finite key analysis, and so on and so forth. And finally, if I can have one last minute, the last topic that we have been working on is the finite statistics of QKD. So what happens here is that security proofs of QKD rely on statistical inference, and people have been essentially reusing the tools from the original security analysis for a while, probably because they had to concern themselves with some harder problems. But the thing is that if you really take a look at the finite statistics, you can finely tune the parameter estimation part, the statistical inference part. And what we did is we came up with very simple analytical tool, and then a very simple numerical tool. And if you put those into the security proofs, what you find is that you can really run quantum key distribution with much smaller blocks, okay? So much less data allows you to distribute a key, and this is critical, for instance, for satellite quantum key distribution. And that's it. Thank you very much.
Okay, since this was very dense and we're running late, may I suggest that you go see those guys at their posters that are outside to ask questions. And we'll continue with Davide Rusca.
So, hello everyone. So I will continue just on. So I'm Davide Rusca from the Vigo Quantum Communication Center, and today I'm going to present you the work that we did in these few years over the line of research that I'm in charge of. So pretty much everything that is presented here has been done with the funds of this project. So like 3 years ago when we first started and we did one of these presentations, we had nothing, no lab, no anything, and now finally we have some results. So this is the group that works on quantum technologies now in Vigo. We have myself, Hugo, that are co-leading this group, Frederick Grunenfelder as the experimental postdoc managing the lab itself, and then our 3 PhD students, Ana Blasquez-Coido, Ainhoa Guillero, and Martina Alvarez. So these are few pictures of the lab itself. Our group is focused on mainly 3 lines of research that, like, of course, this is just an arbitrary division that I'm making, but conceptually it works. One, of course, is QKD, quantum key distribution, in terms of prototyping and to making experiments the most performant possible. One is quantum random number generator, so not only the distribution of key, but also its production in a more secure way and more performant way. And finally, something that goes very hand in hand and with the collaboration with the theory group and with the hacking group, which is the experimental implementation security. So trying to move our prototypes towards the implementation security that can be achieved maybe theoretically, but it's much harder to do experimentally. So just to give a little bit of an idea of each line of research, some works that we did inside of that. So now we have in our labs a running QKD protocol with 1.25 gigahertz of repetition rate. Just lately we have also like a running estimation of the Q-bar and the phase error rate. And the performance that we can achieve, of course, are not as good maybe as the most performant protocol that we've developed also in Geneva, but here the main goal is a little bit different, which is the control of all the variables related to the state encoding and to the detection part, in order exactly to have perfectly in control all the variables in play in order to move towards what we discussed before in implementation security. Then also, always in terms of prototyping, we have our line of quantum random number generators. In this case, what we focused on is what we call semi-device independent quantum random number generators. So we try to leave the characterization of the components that make our experiment at the lowest possible level. In this way, we don't need a characterization. No? If the components are not trusted, they don't need to be characterized. So the idea here is that we achieve some more secure generation of quantum key distribution. Here, like this is one of the examples of the experiment that we use by some homodyne detection by modulating directly gain switched laser. And but then there's like this is just if you want the skeleton of a line of different protocols that can be applied to this, where we don't trust at all the measurement device that we use, and we partially characterize the source. So we try to get anything, like all the assumption to the minimum, without going completely into device-independent regime, where we will lose one of the main goals that we have, which is to remain practical. And finally, like the line of research that maybe we had in the past few years the most focused on, which is this experimental implementation security. So the idea here is exactly the problem that also was explained by Victor in the presentation before. So what happens when you move from a theoretical protocol to an experimental one? So you can see just like this gives an idea, no, that you have something that is very easy to draw on a paper that then becomes hyper complex when you try to put it in a lab. So of course, there's going to be some complex system that has to be analyzed. And what happens if you don't do this passage properly will be explained in the last presentation of our center by Vadim. And here, just to give an idea of the different works that we did over this line, we have some novel technique on the upright to characterize the state with the homodyne detection and tomography of the phase carried out by the gain switch laser, such that we can measure both the encoding flows, but also the correlation both in intensity and phase of the states that we generate. We did a more particular study if we just go down to the right over the intensity correlation that we get in our system if we try to modulate it too fast. So what happens is that now we say 1.25 gigahertz, no, but why don't we go to 2.5 or to 5 gigahertz, no? Like, what are we losing if we do that? Then, like in this study, we analyze exactly the correlation that raises from this kind of procedure. And instead, the two that we have here on the left are more related to actual vulnerabilities that are discovered over these systems. And The vulnerabilities on the top is a vulnerability that it's related to twin field QKD, so to a specific implementation of twin field QKD, if I may say. Then, like where we try to injection lock the laser directly in order to modify the intensity of the states that are produced. And this study was done in collaboration with the company Toshiba in the UK, while the study on the bottom left is on an injection locking attack over a normal or like a BB84-like QKD system. And this study was instead carried out in collaboration with Fraunhofer and HHI in Berlin. So, like, without trying to steal more time from my colleagues that will follow me, like, I thank you all for your attention. Thank you very much.
So we'll just continue right away with Antía Lamas Linares, and all of the members of Davide's group are here and also have their posters outside if you want to ask questions.
Hola, boas tardes. My name is Antía Lamas Linares, and I lead the satellite quantum lab. So this is the last group that was established, last experimental group that was established in the Vigo Quantum Communication Center. We're a small but intense group. We have 2 postdocs. Hannah, who's the senior postdoc, has been introducing the speakers this afternoon. Lucas, who's another postdoc. Alvaro, who's a PhD student, currently visiting a collaborating group in Italy. And Pedro, who's a visiting student from Portugal. We work very closely with the rest of the groups in the Vigo Quantum Communication Center, but our focus is specifically on free space quantum communications, and specifically satellites, specifically applied to satellites. So of course, it has been said several times during the talks today that there is a limit to how far we can propagate quantum information over fibers. And that means that to go really long distances beyond that rule of thumb of about 100 kilometers in fiber, 20 dB of losses, we need to go to something like a satellite, at least until we don't have quantum repeaters. So for example, here you see that to connect, say, Vigo to Madrid, like something under, say, EuroQCI, we would need a satellite. The idea there, it seems incredibly complicated that going to a satellite with single photons would be something easier than anything else, really. But the key thing to understand is that the losses in transmission between a satellite and ground are geometrical in nature. Essentially, it has to do primarily with the expansion of the beam, and that goes with the square of the size, because most of the propagation is done in vacuum. So there's a tiny bit of atmosphere right above the Earth's surface, and then it's vacuum. So we are actually setting up a optical ground station, a quantum optical ground station. This is pretty much similar to an astronomical telescope, but it's optimized to detect signals from single photon signals. And typically those single photons come from satellites in LEO orbit. So these are the low Earth orbit that are satellites that are moving relatively fast across the horizon. It takes them about 5 minutes, give or take, to cross the horizon, and they come around in a typical orbit every 90 minutes or so. Now, one can ask, is Vigo a good place to put such a system? Today, the answer would be definitely no, with the weather. But Vigo actually has a microclimate. It has reasonably good weather. It's a little complicated to make estimates, though, because Vigo is, and specifically where the ground station will be, is at the intersection of the oceanic models for weather and the more inland weather. So we are trying to check those capabilities. Specifically, we have a weather station, let's say a special weather station that, apart from taking the usual temperature, humidity, those kinds of parameters, it also measures the cloud cover in the sky and does some measurements of turbulence as well. What do we need for equipment? I already mentioned several times our optical ground station. That is not there yet. If you go around the campus in Vigo, there's a place where you'll see a platform. That's where the optical ground station will be. It was supposed to be here last week, I think, but it's been delayed by a few weeks. Should be here later this month. So hopefully anybody visiting in a few weeks onwards will be able to visit that. In the meantime, what we have are what we call baby optical ground stations. So these are our telescopes that are smaller in size that we use to prototype and start testing the equipment for those bigger optical ground stations. To give you a sense, eventually the optical ground station will have a 80 centimeter aperture. That is a pretty large aperture, and it's around the limit of how big you can go and comfortably follow a LEO satellite moving across the sky. It has 4 ports for different experiments, so we have the ability to have several experiments permanently attached to the ground station and do different things and switch between them. It will be compatible with both 800 and 1500 nanometer signals. So 1500 nanometers, of course, is the typical optical telecom signals, but a lot of the free space experiments are done in the 800 nanometer range, and several of the quantum satellites out there are in that range. We will have an adaptive optics system, as well as classical optical comms, and of course single photon detectors. Some pictures of so you'll see there on the upper left is the platform where the telescope and the dome will be situated. There is an associated little container that will contain our equipment. It will be a mini lab. So what are we doing along these lines? Well, basically we are doing the design and the prototyping for these links. So you'll see several of the equipment things. One of the aspects that we're taking advantage is that there is a hill nearby, monte, called Galinheiro, and we are doing tests of transmission essentially between here and Galinheiro by setting up a retroreflector there and just trying to image and detecting those signals back. That has to do with the characterization of the turbulence, our ability to correct for turbulence, and so on. Also, another point is that communications like this at ground level are actually a worst case scenario. That turbulence is much worse than when you're pointing directly up. It's harder to deal with generally. We also have work on SPDC sources. So Suso before mentioned some of their work in SPDC sources. We're doing this is the work of Álvaro, the PhD student. He's building a highly degenerate photon source that will emit both in the telecom range and in the close to the visible range using bulk crystals. So this is not integrated optics, but just traditional bulk crystals. And that work is ongoing. And finally, something that perhaps you haven't heard about, and that is that we are using some of the same techniques that we use for quantum communication to do additional tasks. So the idea is that we are putting a lot of effort into these technologies and these structures, and there are quite a few things that one can do with the same hardware by modifying the way we process the data and sometimes modifying slightly the protocols. And one of those things is clock synchronization or time transfer, which sounds really obscure, but is actually of great technological importance. A lot of our infrastructure actually depends on very good clock synchronization. So what we're doing is by slightly modifying the decoy state BB84 protocol, we are able to do time transfer or clock synchronization at the picosecond level with really high resistance to noise and losses. So this is another aspect that we are exploring in our. Right now, that this work is theoretical, but soon we expect to implement it in the lab. And with that, I'm done. Thank you very much.
Okay, for any questions that you might have, feel free to talk to me or Antia during the coffee break, and we will continue with the presentation by Vadim Makarov.
Thank you. My name is Vadim Makarov, and I run the Quantum Hacking and Certification Lab. Quantum communication and quantum cryptography in particular are unbreakable in theory. I mean, you can't break the theoretical protocol. If you implement it as written on two sheets of paper, there is nothing an eavesdropper can do. She is completely cornered by the laws of quantum mechanics. But practical implementations contain imperfections, many imperfections of different kinds. Imperfections of optical components, calibration routines, people make mistakes when they implement the systems. So today we know about 30 different implementation imperfections that actually allow you to break the security of the protocol and eavesdrop on the key. My lab is dealing with that kind of problem, imperfections and attacks based on imperfections. But nowadays that quantum cryptography is actually being deployed on a large scale. Most countries need to certify the cryptographic systems. This certification system is well known from classical cryptography. It's a well-established process. The national government and the National Security Authority comes up with a paper document that is the certification standard that tells an accredited lab, a government lab, what needs to be checked in a commercial product to make sure if it is of a good enough quality to be used in the country. So the government takes care of you or of your cryptography because it's such a complex task that nobody else can really do it, but most countries rely on government. And this certification system exists for all the classical cryptography and now is being established in different stages of being established in most countries for quantum cryptography. So the manufacturer has to submit the system and all the engineering documentation to this accredited lab, and the lab checks if it actually passes, if the countermeasures to known problems are good enough, and so on. There are 3 tasks here that a research lab can do. One task is to help the manufacturer prepare a commercial system for certification. Because if the system contains loopholes and doesn't have good enough countermeasures against them, it's not going to pass this certification. So it's useless to submit it for certification. The manufacturer has to do the analysis and check it first. So I've been in several teams that have been doing this kind of analysis for commercial systems for AtlanTTic, Quantum CTEC, 2 Russian companies. And nowadays we collaborate with another company that develops another QKD system. So we check it, make a list of all the potential problems. You can see this work on poster number 5 in the corridor. Another task is to help write the standards. And there are international standards like ISO standard to which I and my colleagues have contributed. The standard, ISO standard, was published 2 years ago. And the third task is you can help develop a certification methodology for the accredited lab, because the standard is usually not detailed enough, but you need the actual detailed manual and the test benches that the accredited lab can actually use to implement the tests. And in this lab, you can troubleshoot, prototype, troubleshoot in a research lab, publish openly all your results, and then you just say the certification lab, accredited lab, look at my publications. So my lab is participating in all 3 tasks. And another thing, you can look for loopholes in a QKD system, but that's a classical activity. So we are analyzing, currently we are doing security analysis for Technology Innovation Institute in Abu Dhabi, which develops a passive state preparation, short distance QKD system for metropolitan networks. And we are in the middle of this analysis. In my lab, we have 5 certification test benches. I will show you for different kinds of vulnerabilities or prototype certification test benches. Actually, that we have the certification test benches is very helpful for my colleagues in Davide's, Hugo's, and Marcos groups, who actually use them to do some work on developing methodology for EuroQCI. So there is already a interaction between the groups. And then we also purchased IDQuantic commercial QKD system and want to try a couple attacks on this system. One of them is based on Marcos' recent paper that shows how you can eavesdrop on this system or try to break the key. Those are the test benches, the 5 test benches I mentioned. One is wideband spectral characterization test bench that measures the transmission loss of fiber optic components in a very wide wavelength range, because the eavesdropper is not limited to your communication wavelength. She can use any wavelength, so you need to know the performance of your components. And this is an atypical task. And we had to build our own test bench because no metrology institute has it. Another, the detector, single photon detector has many security problems, so you need a detector characterization and testing test bench. Then the characterization of state preparation. So Victor has just shown you the intensity correlations. So that kind of problems you need to characterize the states, and this is how it looks like. Then avalanche photodiodes that are used as single photon detectors have another problem. Each time the photodiode has an avalanche, it emits a flash of light because it has many carriers and some of them actually emit photons. And this is a leakage channel, so you need to characterize those backflashes. And then give the theoretician a number of what the probability of the leakage is. And then laser damage, high power laser damage, the fiber optic components is another attack. If can do, she can try to physically change the components by injecting several watts of power, and this also you need to test. I've chosen to show you just one example of those 5 test benches, and this is sadly the same example that Victor has already shown, because this is a good example of collaboration between theoreticians and experimentalists. So the problem Victor has shown you is the intensity correlations. A typical QKD system, when it runs a decoy state protocol, uses an intensity modulator to prepare light pulses of different energy. And because this is a high-speed electronics that always has limitations of bandwidth, there's going to be intensity correlation between the states. The security proof requires the states to be independent of each other. But actually, if you look, this is an actual oscillogram from a QKD system. And here you see a vacuum state, almost nothing, decoy state, signal state, decoy state. And you can already see that the amplitude of the peak power of the decoy state depends on which pulse preceded it. This is not a fluctuation, this is correlation to the previous pulses. So indeed, if you integrate the energy of each pulse and you plot over many pulses the distribution of their energies, you can see that the pulses which were preceded by the signal state tend to have a lower mean energy than if they were preceded by decoy or vacuum. And then, and to characterize this, we simply set that variable attenuator in the QKD system to 0 to get classical signal, which is then measured by a photodiode and oscilloscope. So you get this oscillogram, and then you simply process it. And Victor has already shown you can visualize the mean energy as levels, with unit 1 being the average level, and then you see that then the levels diverge. If the preceding state was signal, then it's 4%, on average 4% less energy in a pulse, and by the other 2 states it's on average 4% more. And if you look at longer range correlations, for example, take 2 states, then the levels continue to diverge. On poster number 6 in the corridor, you can see the same diagram with up to 6th level correlations. And there are long range correlations in the systems, actually. And then if you give those numbers up to the 2nd range to Marcos Curty's group, they have a security proof that can predict the security rate in the presence of those correlations. Thank you.
Okay, thank you very much. So So next, we'll have the industry roundtable, and joining that will be representatives of the companies Gradient, Thales Alenia Space, Mestre Lab, Bahia Software, and CTAG.
Well, good evening. I hope that you can hear us. It's a pleasure for me to moderate this roundtable. About now, we are moving to technological centers and companies that collaborated with us during these years, developing solutions or contributing to our projects. One thing, I have to start the time. Let me first introduce the people that are in the table. I will start by Eduardo. Let me check the other. Eduardo, that is from Thales Alenia Space, that is there.
Hi, can you hear me? Hi, everybody. I'm Eduardo Bani. I'm from Thales Alenia Space. I work in Madrid, and I'm here because actually we are building a geostationary QKD satellite in the framework of the CDTI plan of Plan de Recuperación, Transformación y Resiliencia. Sorry, I always forgot the name. Anyway, and that's why I'm here. And it's a pleasure to be here. Thank you, Andres. Thank you, Vigo. Thank you, Marcos.
I think that the next one is Gabriel from Gradient.
Okay, so I'm Gabriel Carral from Gradient. We are here to, well, we have a poster also to showcase our results in the PCC in collaboration with Cesga and UVigo. And I work in Gradient as a senior quantum engineer. And we work in quantum communication, so that's why we are here.
The next one is Diego from Bahia Software.
Hi, good afternoon to everyone.
Push.
Yes. Hi, good afternoon to everyone. I'm Diego Beltran from Bahia Software. As we are currently working in the innovation department in quantum computing, so thank you, Andres, for the invitation for today.
The next one is Alexandre Rodriguez from Mestre Lab.
Hello. I think it's turned off. No? Hello, I hope you can hear me. Yeah. So I'm Alexandre Rodriguez. As Andres said, I work as a software developer in Mestre Lab Research. And we're here because our company has made, alongside with Cesga in collaboration, a quantum investigation project on how to simulate NMR spectra using quantum computing technologies. So thank you for your attention.
Finally, but not the least, is Carmen, but in this case, I moved to Spanish because she is not comfortable with English. So, Carmen, por favor,
entre ustedes.
Sí. Hola, yo soy Carmen, soy por el Centro Tecnológico de Automoción de Galicia y bueno, estamos aquí gracias a la invitación de Andrés y bueno, no me siento muy cómoda hablando en inglés, con lo cual me voy a explicar en español.
Well, first of all, thank you very much for being here and for accepting our invitation. I know that for some of you it's difficult to be here because it's far from your workplace. But in any case, I will stay with Thales Alenia Space because you have a very nice project that is Garbo. Okay, so in case of your company, how do you see the future of this technology, the QKD technology that you are developing now?
Okay, first of all, it's a very pleasant name, but our client, CDTI, doesn't like it. So we are rebranded as GeoQKD. So, but anyway, actually we build satellite as Thales Alenia Space. And we build all space-related stuff, from satellite to space station to whatever. We don't do rockets yet. We will do in future maybe. Why we do QKD? That's a very clever question. We don't know, but someone came to us and say, okay, we need a quantum link between two cities, and we ask, in a satellite, right? And they say, yeah, sure, for sure, in a satellite. So we built QKD mainly because we close the gap where the fiber cannot arrive. So fiber has a limitation depending on which technology you implement, but when you move to satellite, you cover large portion of the Earth. And if you go just stationary orbit, you cover 1/3 of the Earth. So yes, with 3 satellites is always the theory. With 3 satellites, you can cover the whole Earth, and you can provide services to all the people that want to pay for your service, actually. So we build satellite, we build QKD satellite to close the gap, and we actually see a bright future for QKD, especially in Europe. Otherwise, we will not be there. And we implement in Madrid. We are implementing photonic labs, not as big and as wonderful as those here in Vigo, but we are starting. In all the other sites on the company in France and Italy, we do have also deployed and implemented some QKD, and we are doing QKD there. And we are a major player in VQCC in Spain with GeoQKD. We are a major player in other European projects. So yes, we saw an opportunity, a business opportunity there, and we enter.
Okay, thank you. Let me move to Gradian, because Gradian is somewhere in the telecommunications sector. So which is your view about the future of the technology, the quantum technologies in this sector?
Okay, so just getting from the telecommunications sector, which is the main area of activity of Gradient. On the side of QKD, we see like two main improvements. First is to make QKD, put it everywhere. So for instance, in the case of satellite, QKD is quite paradigmatic because with this new space, like the industry, space is getting like full of private initiative. So to provide a QKD service within a satellite, especially small satellites, needs a lot of improvement of QKD to make it like miniaturized and compact, so cheaper. And I think that's one of the routes that QKD should take or may take, which is making it like less expensive and less massive, so to speak. And on the other side, there are also in quantum communications in general, I will say that what is required is this development of enabling technology like quantum memories or quantum repeaters that will take a step forward and like devise a full-fledged quantum network, which also involves computing, sensing, and QKD, of course, as a part of it, a security part of it.
Okay, I have a question for both of you, because today we have seen different proposals for solutions. One regarding the use of fibers in order to cross, for example, the Atlantic Sea between Europe and USA. But there are other possibilities that use satellites, geo satellites. That is the project that Thales is developing, and or you cited they use the low orbit satellites. My understanding is that these technologies are complementary, but we have seen, for example, in the previous presentation that the clouds can be a problem for the satellites. So which is the solution that you can see for the future? Satellites, mixing technologies?
Definitely. I mean, as I said, geostationary satellite covers the Earth, but only cover a portion. So, and are very stable, actually. So, when you start to illuminate a portion, you actually point the telescope in the satellite, with, for example, in Madrid or in Vigo, and we hope in clear sky. You point the satellite, and you can maintain the link virtually forever. Obviously, there comes some limitation, like you've got the sun, you've got some intrusion in your satellite that can damage the equipment, and then obviously you can go in a bright, you can go in a daylight bright, and that can be a very dramatic problem since you got more noise. Depending on the technology that you employ, it can be a very limiting factor. So virtually, the geostationary gives you the stability for those area on the Earth where you can have very low clear sky and you wanna keep all the key material that you may distill in those very few moments on the Earth where you can do it. So this is the main advantage of the geostationary. On contrary, it's costly. I mean, it's very costly, a geostationary launch, not only building the satellite, that maybe no, it's costly even that, sorry. Everything is extremely costly, and going for a LEO solution, it's actually the complementary side, where you can have higher detection rate, since your link budget is better, definitely, but you have got the limitation of the field of view of your satellite. So there are complementary technologies. It really depends on the use cases. We use one or the other. So it's easily one operator, that could be a telecom operator, can be a satellite or not, should implement both technologies to provide a useful service for their clients, obviously. But it really depends on the money that those operators has and what are their users. So it's really depends on the use case, using one technology or the other.
Yes, I just want to add, in the low Earth orbit case, yes, you're limited to the overpass of the satellite on top of your ground station, and if there's pollution, like solar pollution, or the sky is cloudy, will decrease your key, your distill key, so you have to accumulate key and like predict the demand according to your customers, how it will be, so you always have key to give them and establish the connection. But yes, there's a lot of effort in like trying to put all this technology into a service that some people find useful and pay for it. But yeah, the LEO case, you can, the advantage is that you can put smaller satellites.
Okay. We have to move to the computing part. So I will start with Diego. Diego, your company developed a solution for distributed quantum computing, that is Polypus. But we are curious about why your company has selected this area of quantum computing for the future business. So can you tell me more information about that?
Yes. So thank you, Andres. Us at VIA Software, as we have an innovation department where we specifically work on new state-of-the-art technologies, we have the capacity to experiment with new technologies without any interference with our business products. With that being said, from almost 2 years ago, we decide that quantum computing is going to be extremely relevant in the near-term future, we strongly believe that it's going to be applied to many different use cases: industrial optimization, advanced simulations, quantum communication, of course, and quantum machine learning. In some of those areas, we strongly believe that some of them are going to be very related with some of our business use cases. And that's why we decided to enter in this early stage, because we believe that as it has a significantly steep learning curve, we strongly believe that being able to start using quantum computing this early, we are going to have a competitive advance regarding other companies when the clients start to demand quantum computing. That's basically our main focus now, to be prepared to when the market, the clients start to start questioning about quantum computing.
Thank you. The time is running very fast, so I have to move to Alexander. You are a consumer of the quantum computer mainly because you are a leading company, you work for a leading company in the sector of analysis or in R. So why, well, not why, what do you think about the experience that you had using quantum computing for your area, and which is the prospects for the future in your opinion?
Okay, so I would like to just give a very brief insight on our company. So as you mentioned, with all of the tools that the biotech sector uses to analyze the NMR spectra, which is a physics experiment of spectroscopy. And I think it's, because of that, we are always working hand with hand with the necessities of the biotech sector. And for example, our case of use is the simulation of an NMR spectra. And in that scenario, the classical solutions are sometimes a bit limited because sometimes some calculations are too costly and cannot be tackled with classical solutions. So I think quantum computing is interesting because it allows us to surpass that classical limitation, okay? So that means, for example, a pharmaceutical now can work with bigger and bigger biomolecules they can discover. Now they are going to have the tools to work with that, thanks to quantum computing. I think that maybe the most use of cases right now maybe we do not even know, because I think it's going to open such a new area of possibilities. Okay. And I think that it's very interesting in that context that I do think that, classical computation can still be used, but I think there are going to be certain big, difficult calculations that quantum computing is going to allow to perform better. I think they can coexist, okay? But mainly it can, like, now we have more tools, we have a bigger space to explore.
Okay, thank you. Carmen. Bueno, Carmen trabaja en el Centro Tecnológico del Automóvil, un sector importante en Galicia y en España en general, y bueno, tenéis mucha influencia en la parte de la electrónica, por ejemplo, para el sector automóvil, entre otras áreas, ¿no? Pero como consumidores de tecnologías cuánticas, que tenemos varias, con computación, comunicaciones, sensórica, ¿cómo veis desde el CETAG estas tecnologías, cómo se pueden incorporar?
Pues, bueno, lo que estamos viendo ahora mismo es que, bueno, nosotros somos consumidores de tecnologías en el amplio espectro de la palabra, ¿no? Yo trabajo sobre todo en lo que es los procesos industriales, en los que, bueno, cada día se tiende más y más a hacerlos pues, automáticos, robóticos. Entonces, todo eso, la manera rápida de poder hacerlo, necesitamos unas comunicaciones muy, muy ágiles. Entonces, una parte importante de la cuántica es la comunicación, la rapidez de las comunicaciones. Por tanto, el poder, por ejemplo, hacer una programación robótica desde cualquier punto del mundo, pues cuanto más rápido lo puedas hacer y sin ningún tipo de interferencia, pues evidentemente va a ser mucho más eficiente. pues, por ejemplo, la parte de las comunicaciones. La parte de la sensórica es más de lo mismo, ¿no? Ahora mismo necesitamos tener todo sensorizado, necesitamos que todo esté controlado, monitorizado. Por tanto, la sensórica cuántica, muy, muy importante también. Y la parte, bueno, la parte de la seguridad. Bueno, la parte que está muy ligada a la comunicación, es muy importante la seguridad que puede aportar ahora mismo la cuántica frente a los métodos tradicionales y clásicos, donde, bueno, aparentemente y se ve que cualquiera puede manejar la información que está ahí. Por tanto, creemos que la tecnología que nos da la cuántica va a ser muy importante en los próximos años en el sector.
Vale, no hay problema. Nosotros colaboramos con vosotros. Nosotros
encantados.
proporcionamos el robot y el sistema de control y vosotros que no tengamos accidentes. Nos quedan solo 2 minutos, entonces una respuesta rápida. Voy a hacer la pregunta en castellano para que la entienda correctamente. ¿Creéis que las tecnologías cuánticas son las tecnologías disruptivas que se han propuesto para el futuro o realmente nos vamos a quedar a la mitad?
Empiezo yo. Vale. ¿Contesto en castellano? No hay problema. Sí, personalmente sí, claramente. Juegan un papel importante. Avances en computación cuántica, aquí de los compañeros, son fundamentales y necesarios. Y claro, cuando avanza eso hay que proteger las comunicaciones. Y entonces, de alguna forma, entre post-quantum cryptography y QKD, tienes que cubrir esas desventajas que puede cubrir la eventual llegada de un ordenador cuántico y algoritmo Thor, de Shor, bla, 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 bla.
Yo creo que sí, que son...
Que nos queda un minuto.
Rápido. Yo creo que sí que van a ser muy rompedoras, tanto computación como comunicaciones, como sensado, que muchas veces se olvida, pero es una tecnología muy madura y creo que, bueno, las tres van a ser súper importantes en los años que vienen.
Bueno, nosotros, sobre todo donde consideramos la computación cuántica, es como había anunciado también el Cesga en su charla, que es en el entorno integrado en centros de HPC. Si consideras que la computación cuántica es un acelerador, como en su día o a día de hoy son las GPUs, en ese caso sí que creemos que va a ser disruptiva y que va a aplicar a prácticamente todos los sectores.
Sí, yo creo además que... creo además que, por ejemplo, en el ámbito de la química, es la famosa frase de Richard Feynman, ahora es que literalmente tenemos una tecnología que nos va a permitir recrear tal cual lo que estaría experimentando la molécula en un ordenador y podemos avanzar en este proceso del laboratorio in silica. Vale.
Me están llamando la atención.
Vale, yo solo voy a decir que sí, vale, así que soy súper corto, que sí, evidentemente creo que tenemos que ir por ahí.
Muchas gracias por participar. Ha sido muy corto porque nos han dado solo 20 minutos. Estoy seguro de que podríamos estar aquí 2 horas. Pero bueno, ahora tenéis la oportunidad de discutir. Creo que tenemos un café ahora, ¿no? Entonces, yo creo que tenemos una posibilidad de que podáis preguntarle más cosas directamente. Y bueno, muchas gracias de nuevo por acudir y pues dar respuestas.
Gracias.
So actually, maybe you guys can stay seated for just a second. We've made it almost to the coffee break, but I would like to ask everyone to come to the front so we can take a group picture real quick. And then after this, we'll have a 20-minute coffee break.
Tenemos oficinas en toda Europa y las oficinas están en iguales campos. Bueno, ya ladito hay muchas empresas en 3 campos. Sí, es muchísimo espacio. Ana, Winston, for example, yeah, maybe.
Final part of our meeting today, we will have Marcos Curty giving us an overview of the Quantum Hub and some other ongoing initiatives, and then we will also hear the final words today from him.
Okay. Hello. So I know we are already late, so actually I'm going to try to be then really fast. Let me say the main purpose of this part was essentially just to show among all of us what are the initiatives we are involved. Okay, just to have an idea, because one of the main concerns that we had when we started the Planes Complementarios is what will happen afterwards, no? And how we will continue. And then we just wanted to we have asked for all the initiatives that the groups in Galicia, the 3 universities, Coruña, Santiago, Cesga, and Vigo, we are involved, for 2 reasons. First of all, to see that indeed we are doing very well, and all the possibilities or all the projects that participating in Planes Complementarios has helped us, and also at the same time to be aware of what other people in the community in Galicia are doing. But as I said, we are running out of time, so I'm going to try to be quite dynamic, because I also expected just to present 4 or 5 projects, but actually I was very surprised that, I don't know, there are around 20 or 20-something projects. So there are too many to enter in details, and it would be just at least one after the other, that it doesn't make too much sense either. So I'm going to try to go through them, but kind of highlight some that I believe are quite relevant, and others I will also mention them, okay? So, and also let me say that the projects that I'm incorporating here, or that I'm showing to you here, are projects that are currently running, because they are, with the exception of 2 that appear at the end, that people have recently applied for them, I have received false information from many other projects that people have been applied. And these ones are not included. So I essentially just include the ones that are running at the moment, except for 2 exceptions at the very end. So, and the title was starting with Quantum Hub and other initiatives, because this Quantum Hub initiative has been quite relevant recently in Spain, but actually looking to the initiative that has been incorporated in the file, there are many that are equally important. So maybe the title should have been Other Initiative in Quantum Information and Quantum Technologies in Galicia. But just briefly, and as I said in a kind of fast and quick way, let me say that the Quantum Hub was a way that the ministry thought as a first way to give immediate continuation to Planes Complementarios, to try to make a kind of, let's say, to filling the gap for a few months. Because actually, if you see the project, it actually runs only till summer 2026. So it is really a project that in principle sounds very ambitious, because it has very ambitious ideas, again, to make a very strong collaboration between different entities in Spain. But if you look to the timeline, it's so short that actually is not possible. So at the end, the hub is going to be another tool to really extend contracts of researchers, and also to get new infrastructure for the labs and so forth. So, but you have here the list of the institutions that are involved in Spain. There are 3 main pillars, but essentially there are one part of use cases that is essentially preparing optical ground stations. There is one already in Vigo, there will be soon, as we said, but they want also to put an optical ground station in Madrid and one in Barcelona. And many of the use cases or the budget of this first line is about preparing these optical ground stations to be able to connect to quantum satellites. Then there is a second part, that there is a kind of mixture of different topics, from quantum communication protocols, from repeaters, memories, integrated photonics, and so forth. That, again, the idea was really to make a research project in a collaborative way between the different partners, but in reality will not be the case. There is no time for that. So we will do the best we can, but it's not really expected much collaboration. And then is one third pillar about, let's say, training. And in the case of training, there are 3 main activities. One of them is to buy some equipment that we could use in our teaching labs. For instance, here in Galicia, we are purchasing some material that we are going to use in the master that is coordinated by Javier Mas, so that we can use it in the Galician master, but also in other parts of Spain, they're also getting some equipment. There are some part that will be also some seminars for companies and so forth. And there is this Taller de Trabajo Nacional that is a bit unclear, is actually to try to organize some meetings between young researchers and also startups and industry to try to discuss and make also some training activities about quantum technologies. This is more or less the idea. And just to be precise, in Vigo, most of the budget that we are getting will be invested in improving the optical ground station. You see there the picture, Antia presented it this morning. The picture she presented was a bit older because they didn't have this nicer shield that now you see there, but it still doesn't have the optical ground station yet. That will come hopefully in 2 weeks. And there are different devices that we plan to buy with the hub, including, as you see here, the pointing system, an adaptive optics system, and some other tools for the labs. This is essentially what we are using the Quantum Hub for, at least at UVigo. Other initiatives that are relevant in Galicia, we have the Iberian QCI, in this case with the participation of Cesga and the VQCC. And as you know, there is now a link deployed between Santiago and Vigo, so with a commercial system that is running, and we can use as a test bench also for research. And eventually, there are plans that maybe one can extend this network in Galicia, maybe connect with Coruña, maybe with Lugo, etc. But within the EuroQCI, there is the plan to have a network also in Portugal. And also there is a metropolitan network in Madrid and one that is growing in Barcelona. And the idea of this project that is starting now and will run for 4 years is to connect Galicia, in this case through Vigo, with Portugal, with the EuroQCI in Portugal, and also eventually connect with Madrid and Barcelona, hopefully through the OGS. Of course, to connect through the OGS, you need still a satellite. There is no satellite yet, but we expect that we could use, hopefully, the ones of ESA. Okay, this is more or less the idea. Other project that is relevant, that we are many of us involved here, is, Vadim was mentioned about certification. There is a huge activity in let's say, promoted by the European Commission to try to certify quantum communication systems. So providers really need this certification authority that guarantees that the system comply and they are really secure. And this project is called Nostradamus. There are many partners involved. In the Spanish institutions are the one you have there. And essentially, we are working strongly on Nostradamus and helping to design the methodology test that one should implement to the devices to guarantee that they really comply and are robust against main vulnerabilities or main known vulnerabilities. Another project in which we're involved in Galicia is Saga. Saga is, there are two main missions in ESA regarding quantum satellites. One is Eagle 1 and one is Saga. Saga is a kind of the next generation, and they are taking it more seriously to make it, to guarantee the security. And this is a very ambitious project, and here in Vigo we are collaborating in Saga. We're responsible essentially of all the part related with the quantum security, so to make it the security proof for the protocol that is being implemented in Saga. Although I must say that this project is particularly problematic working with because Saga is classified, so that means that things cannot be open, and this makes the collaboration quite hard. Then other projects, very quickly, there are projects, so we have been participating, you know, in the EuroQCI, we have been participating in the design of the architecture for the EuroQCI, for the European Commission, and now there is a kind of project that is coordinating all this deployment around Europe, that is Petrus. We are part of Petrus. We are working also in projects in Europe for the development of a LEO satellite, in this case for the European Commission. We are part of the main project of quantum communication, the quantum flagship, that is QSMP, in this case coordinated by ICFO. So, and in the case of QSMP, the main goal is to develop essentially a technology that could be included in the EuroQCI. So there are also, in the case of Vigo, we are also coordinating a Marie Curie on quantum safe internet. In this case, what we are doing here is combining, there has been two fields that has been working apart, that is the people of quantum cryptography and quantum key distribution, and the people who works more on classical cryptography and now evolve as post-quantum cryptography. And there are no breaches. Actually, there has been many, let's say not many, but there has been certain disputes or misunderstanding between both communities. And here in this project, we try to bring together experts from both communities and try to make some interaction and to try to come together to common grounds. So there is also people here in Galicia are working with a Japanese company NEC, and they are working, in the case of the group of Suso Liñares, they are working in quantum communication in submarine networks. So more projects that we have here in Galicia. There is a Quantum Excellence Center. This is mainly run by many of the institutions here. We have Cesga, Santiago, CITIUS, IFCAI, Coruña, CITIC, and so forth. And as you see here, the main goal, I'm not involved in the project, but I was looking into it, and my understanding is they want to put all together many different resources that we have in quantum computing and in quantum software and so forth, to put them together in a kind of common umbrella, that there is a kind of common coordination among all of them. So, and this seems a very interesting project as well. Another project, in this case led by Cesga, this is gravitational storage, quantum computing, and AI for a cleaner energy future. And my understanding is essentially they want to address the problem of getting more efficient energy and more efficient storage of energy, and try to go towards more green energy using different tools. In this case, quantum computing, gravitational storage, and AI. And understanding is that quantum computing and AI are probably used for optimizing many of the protocols that you could use to distribute or to storage energy. Okay, so this is more or less the idea. There is another project led by Cesga and with the collaboration of Gradient here. So, and in this case, the idea is, well, essentially work in quantum machine learning, that they have a lot of competence here in Galicia, in particular in Cesga, and also to develop a hybrid algorithm for quantum and classical, combined quantum and classical algorithms, some hybrid algorithm for getting some advantage, quantum advantage. So then there are several projects that are coming, let's say, from the ministry directly. Here I just mentioned very briefly a few of them. Well, there is the project of GEO. This is not a minor project. This is actually a very ambitious project, but this has been already presented by Eduardo, that is here in the audience in Thales, is the first one. So we know this ambitious project to go to GEO. Then we have also projects from the ministry to try to make quantum communications simpler and more secure, and let's say more practical. There is a project also with the National Security Agency in Spain also to develop, let's say, tools for certification of quantum technologies. We have a project about deep quantum related with quantum computing that is led by Cesga. There are also projects led by the University of Santiago, mainly related with integrated photonics, as you see, with chips and integrated photonics, and different two projects of them, with the second one with very strong funding. And then also here at the University of Vigo, AtlanTTic, sometimes there is some confusion because the Vigo Quantum Communication Center is also part of AtlanTTic, but we have kind of our brand, but within AtlanTTic. But there are all the researchers in Vigo, and particularly in AtlanTTic, who are interested in quantum technologies. And this is an example. Manuel was here before, and Anna. And they are also working from the point of view of using QKD, but from more an engineer perspective. And this is a project that they are leading at the moment. And to finish with, I have just two more projects. And the ones I mentioned so far, these are projects that are currently running. So, and the last two are projects that we have applied for, and we are just waiting for the results. This is one of them. This is the PopTech. And actually, this is a project that involves most of the Galician ecosystem. So all the institutions were involved in this PopTech project. So we have here Cesga, Santiago, Coruña, Vigo. And well, it has a really strong budget, so we are all optimistic about it, but we don't know. So right now it's in evaluation, so we don't know whether we will be successful or not. So let's keep the fingers crossed. In any case, the solution should be known any minute, so it should be quite soon. And there is another project. This is more related with training, and this is, there has been, through the Quantum Flagship, there has been different initiatives in training on quantum technologies, and this seems to be, this Quantum Skills Digital Academy seems to be the natural extension of previous initiatives. This is mainly run by Santiago. There are other partners in Spain, but the main leader here in Galicia is Javier Mas, that is, again, here in the audience, so if you have questions, you can ask him. But essentially, it's trying, again, to coordinate all these resources that we have in education, in quantum technologies, at different levels at the European level. So, I think with this we can conclude. As I said, this was a very fast overview of the projects that are in Galicia, but I think it was enough to show that I think we are doing very well, so that all the partners are involved in most of the initiatives, both at the national, European, and international level. And with this, I wanted also to say that I've been asked to close the event today. This was not planned, but so that means I didn't prepare any particular speech or anything like that. But I wanted to say that, as I said at the beginning today when we started this event, that I think we have many reasons to feel very satisfied and very proud of what we have accomplished. So today, talking with some of the people, and again, Javier Mas was one of the pioneers in Galicia here who started in the early 2000s organizing some schools on quantum technologies with a few students, how things has been evolved in these 25 years, so that eventually we are growing in a community here in Galicia and in Spain and in Europe, but now that we are here in Galicia talking about these planes complementarios, that we are growing in a solid and strong community, that we are also making our links stronger through these programs like planes complementarios and through many other initiatives that I have presented today, as you saw, that involve many of us. So, and this is, again, reasons to be proud. One of the questions that we always think is, now what? No, what will happen after planes complementarios? During the process, during the project, we had among the coordinators of the different institutions several discussions to see what we could do, how we could pressure a little bit the regional government or the ministry to try to get some additional, some extensions, some, let's say, planes complementarios B, and so forth. In the meanwhile, we have not succeeded yet, although as we have here today from the representative from the ministry, he's very happy, or the government is very happy how all the plans, complementarios, not only the one on quantum technologies or quantum communication, but all the others has been running, and the idea is to try to give them continuity. So I really expect from what he has told me today and what he said here in public, that we can expect that these plans will have some continuity. So maybe in the eventual next 2-3 years, maybe there will be a tools with less funding, and hopefully a new tool with, again, enough funding will come along the way. But the good thing is that makes me very optimistic is what I just presented now, looking in how many projects we are involved at the minute. So that means that right now we have guarantees that we will continue our research and keeping improving for certain in the next years. So I wanted to thank you then all for coming today. I hope you really enjoyed the session, and I really looking forward to all the things that are still ahead of us, and that I'm sure we will address them very successfully as we did in the past. Thank you.